Test, test. Hey, it works. Hey. Okay, it's 11:30. I'm sure people will show up an hour later because they didn't set their clocks right. Okay, so let me get started. My name's Steve Rosted, Linux kernel developer. I work for VMware in their open source department. They still let me work on ftrace and other kernel development, the real-time patch, so I'm still very much involved. And we also have user utilities that I'm going to talk about that interact with ftrace. And so this talks about debugging your kernel, or debugging your Linux kernel using ftrace. First off, this is not a tutorial. So don't expect to be like, oh, I'm going to leave here knowing everything. The purpose of this talk, and I have my glasses on here. Before I do anything, everyone has to smile. This is a real selfie. I'll post it online. Make sure it worked. Awesome. Shows how sparse this room is. So anyway, this is not a tutorial. It's more of like, my goal here is so you can kind of have an idea of what's out there that you could actually spend. I have given tutorials. I did in New Zealand for LCA, but this is not a tutorial because I have a lot to cover and you won't be able to keep up. But you can try. So, how many people know what ftrace is? Okay, actually, how many people don't know what ftrace is? Don't be afraid. So almost 50-50, good. It's the official tracer of the Linux kernel, as it says over here. You have it most likely, if you're running Linux, you have it on your machine. If you have an Android phone and you root it, you have it on your machine. Android actually keeps it enabled because they have a lot of tools that uses ftrace. So it's everywhere. And it's really easy because you don't need any tools on top of it to actually use it. If you know echo and cat, you know how to use ftrace. That's the two tools that you need to be able to use ftrace is echo and cat. But there's other tooling I'm going to start talking about that makes things easier because echo and cat could be very kind of difficult to use and tedious. And we'll go through that as well. So again, this is not a tutorial, so I'm going to jump right in. We'll learn from examples. So we're not going to get bogged down in doing all the learning that's going. So just sit back, relax, enjoy the show. First, I'm going to go over just the basics, which is ftrace itself is a fully functional tracing, but the two most commonly used features of ftrace are something called tracers and events. And they're not mutually exclusive, you can use them together. Tracers are sort of a general functionality. You have the function tracer, which basically allows you to trace any function within the Linux kernel. Well, almost any function in the Linux kernel. Any function that's not inlined by GCC. And also any function that you don't specifically say do not trace. I'm going to talk about function graph. There's other tracers that do preemption or that will check for latencies, like you could see how long interrupts have been disabled. Those have more overhead. Those are not usually enabled in production. Those are more debug kernels. We'll be able to have, like, you don't want to trace every single time you have interrupts disabled and turn on because that code is actually highly optimized, and putting any tracing infrastructure in there can cause problems, even if it's just a single no-op. Events are basically single no-ops scattered throughout the kernel that ftrace dynamically will actually turn that no-op into a jump to some code that actually do tracing. So when tracing is disabled, it basically has zero overhead. I've compiled with trace events enabled enabled but not running, so they're all no-ops. And then I compiled without them and done a bunch of benchmarks. Everything's within the noise. So enabling events is not a problem. Sometimes you have to worry about cache overhead because it does inject code within the file. So even though it's not executed, it may spread out the code. So your instruction cache, if you guys know what that is, may fail a little bit more. Interesting enough, when I first wrote events, when I enabled the events, I did a bunch of benchmarks without the events. Then I added the events, I did a bunch of benchmarks. They were actually better than without it. So actually it lined up the cache to be more efficient by putting little spaces inside the kernel. I don't know how that happened. I couldn't figure it out, but that's just how, cache is just a black box. It's magic, black magic. But events, they have all sorts of different events. Scheduling events, interrupts, exceptions, wonderful things. So where do you find ftrace? I said ftrace is on your box, so where is it? Where can you find it? Well, usually most distributions already have it mounted if you're root. Ftrace is basically it allows you to see the internals of the kernel, how it's working, which means that only super user could access ftrace. So you have to be root, you have to do sudo or whatever you want to do. It would be devastating to the security community if we ever allowed users to actually have full access to ftrace. Ftrace is basically the way to get around security. Rootkits love ftrace. No, I didn't say that. It wasn't recorded, right? Anyway, the way, if some people don't like to mount the debugfs directory because debugfs gives you the world of everything it's debugging, even though debugfs is root only, you really found that was recently happened, well, within a couple years. We don't want to mount, some people don't like to mount debug because it adds a lot of access to the kernel that some people don't want available to even for root. So, but they want tracing because perf relies on it, if you know about the perf tool, and PowerTop relies on it. So utilities rely on tracing, so where can you find it? So what we have is I created a tracefs file system to separate it from debug. Although if you mount the debug file system, the trace file system is mounted in the exact same location it used to always be for backward compatibility, but you could mount it directly. If you have ftrace enabled in your kernel, you will know by looking at the directory syskernel tracing, that's a pseudo file directory that will be created from the sysfs file system if tracing is enabled. So if the tracefs exists, that directory exists, and that's where you want to mount it because tools will look for it there. So once you get it mounted and you go to that directory and you do ls, you see this lovely set of, my thing doesn't really work very well. You see all these files. The highlighted ones are kind of some of the more important ones, but don't worry about seeing them, but there's a lot of files in there. This is the API, this is the interface into ftrace. So, for example, if I want to trace functions, if you have your laptop open and you want to try it out right now, whatever, you could. If you want to mount the tracing file system, or if it's a debug file system, you're a root. In my slides, whenever I'm root, I always have that little hashtag as the prompt, because I don't do sudo. I never found why sudo actually is beneficial. I just su to root and do my work and then exit. I don't want my user account have access to root commands. You know, that's even if you have, because you crack my password and you get my user account, you know, if it was sudo, you could actually crack into a bunch of root commands. So if you get my user account, which is what I always do all my real work in, you have no access to the root facilities, because I'm against sudo. I've never understood that idea. Maybe someone else could tell me later on. But hashtags always all root commands. So I would cd into the tracing directory, and I just echo function into current tracer. If I want to stop it, I echo no op into the current tracer, and that will actually disable it. And this is the output. So after I do echo, there's a file called cat, and then boom, you can see all the functions that are running in your kernel live. If you cat trace pipe, it'll actually, it's a producer consumer, which will just run forever. There's a difference between, there's two files, there's trace and trace pipe. Trace is not consuming. In fact, when you read the trace, it actually pauses tracing so it could actually iterate it. So if you stop tracing the trace file, you could read multiple times and it'll give you the same output every time. Trace pipe is a producer consumer. You read it, so it's made to be read while tracing's active. So it won't affect tracing, so reading trace pipe will give you the same output, but if you read it a second time, that output that you read the first time won't be there. So, say if you were tracing and you want to stop tracing, you want to stop the buffer writing. Something happens, you want to stop it so you can look at the trace file. There's a special file called tracing on, and all you have to do is just like echo 0 to tracing on. That's how simple it is. If you want to turn it back, so that stops tracing. It only stops recording. So function tracing is still happening, but every time it goes to allocate, when it goes to allocate space on the buffer, it gets a null pointer saying nothing's been allocated, and then it just jumps out. It says, oh, I don't have a buffer, let's just go on. So it doesn't actually stop the overhead. So tracing 0 on there only stops the recording, but any tracing that you have enabled will actually still have overhead onto your machine. So you really have to make sure you disable tracing, even though the trace isn't doing anything, if you really want to make sure your system's back to normal. Word of caution. Be careful about that space you do. I've actually had major kernel developers tell me that this tracing's broken, it's not working. I keep doing this, I keep getting error on write. Why is this not working for me? How many people see the bug? Got a few. Okay, who really doesn't really understand this? Why one works and the other one does not? Yes. You are writing standard input and standard output respectively into the kernel. So you're just actually, that's a redirect. It's a special, echo 0 with no space greater than is actually a bash command saying to redirect. So I've seen actually major kernel developers saying this isn't working. I go over like you need a space. And they're like, that's just caution. So function tracing, as was mentioned earlier, does not give you any parameters. It doesn't give you any data except a function call was hit, and it tells you who called it. Very informative. You can see the functions, you can see the flow of command, but you don't get any extra data out of it. You just see, oh, this was called. But if you want to get more information, you want data, you want to see variables, you want to see a little more information, that's not supplied. But the static trace events throughout the kernel is used by the system developers, and they will come up and create, put in little hooks, those no-ops that turn into actual tracing, and they'll be able to see information that, like for within their system. Forks, an interrupt goes up. What interrupt was it? You know, so you see, it's okay. It's my Wi-Fi device is going off like crazy. So the way you do, there's a directory called events in that tracing directory. By the way, anytime you see commands, most likely right now it's kind of in that tracing directory until it's not. So if I were to ls events, these are all the systems that are, all these trace system events that are in the Linux kernel. And I'll let you know, by the way, I'm not the one that creates these. I'm the maintainer of the tracing system in the Linux kernel. But when a new event or new tracing stuff, I usually get CC'd on it, and I will make sure they're doing it correctly. But all these events, all these systems and events were created by the maintainers of those events. So they actually are the ones in charge. They're the ones that know what data is good to look at for debugging or whatever. So it's not me just going to put it in. This is all done by the maintainers are doing it. I've added several myself because I actually don't just maintain tracing. I help with this, scheduler and some other interrupts and stuff like that. So I have my own trace points there, but that's just as a different role, not as a tracing maintainer, but as a different role. So how do you enable tracing events? So say if I want to enable this wake up event. So when a task wakes up another task to go run, so if something blocks on an event, something's got to wake it up. So I want to see when that's woken up. So it could be just blocks on an I/O device, and I'm waiting for this. You do a read from a hard drive or something, and it goes, puts the request in, and then it goes to sleep, waiting for the read to come back, and then the interrupt goes off and wakes up your process to read from the hard drive. That triggers the wake up event, and you can actually see it actually happen. So I want to see that event. I just simply do echo 1 into events, sched system, sched waking / enable. Enables events. By the way, I will post these slides up online right afterwards. I just finished these slides literally 2 hours ago. So I'll be posting them up online right after this talk. If I want to enable all scheduling events, I don't care, I want all of them. I just echo 1 to them. And if I just want to enable all events that are defined in the system, I just do echo 1 to events enable. Back, if I have all events enabled, but I want to disable some, I could disable individual ones, or I could disable them by system, or disable all events in one shot. Even if they're not all enabled, you just echo 0 to events enabled, that will disable any event that happens to be running. So, what type of things do you want to do when you debug a kernel? Well, there's performance issues, warning messages, hung tasks, corrupt data, kernel crashes, even at boot up. All this has been used, ftrace has been used to debug. And I'll give you some examples. I can't do everything because it's just too overwhelming for an hour talk. So, for a simple thing, I'm going to start off for a simple example. This is one of the things I like to do because it's something I kind of run on myself, is I always like to see how long interrupts last. Like, if you're familiar with how an interrupt works, I'm not sure what the skill level is here. I think most people, how many people really don't understand interrupts? Just like if you want, so a couple, okay, I'll do a real quick thing. So basically, when you type on your key, the keyboard, when you hit the key, the device is going to send a signal to the CPU. The CPU is going to stop whatever it's doing if interrupts aren't disabled. It'll stop what it's doing, jump to a handler that's associated to that vector that was caused by the keyboard touching it, and then it will run the the code to handle the key, and then it'll most likely wake up whatever process is waiting for key input, and it'll put it into the buffer. So if I hit A on my keyboard, it'll put A into a buffer, and then later on your process will get an interrupt will happen. It'll put it into a little buffer, and then you go and you look at wake up your process, your console, and the console will say, oh, there's something in there, A. I'll read it A, then it'll display A to your video command. That's a basic overview of interrupts. So I want to do interrupt latency. So what I do here, I use this to define, see what interrupt latency is. So I know in the Linux kernel, there's this thing called do IRQ. So it's a function within the kernel that all device interrupts. Timer interrupts don't use this, so there's another function, but just all device interrupts go through a function called do IRQ, which is basically called once the trigger, it jumps this, and that's what figures out what device triggered the interrupt. So I echo that into set ftrace filter, which filters. I only want to trace this one function, so I don't want to trace anything else. I only want to trace this one function. I disable tracing because I want to do two things at the same time. I don't want to start one without the other for recording. So I disable tracing, so I echo 0 to tracing on. Then I'm going to enable the function graph tracer. The function graph tracer is similar to the function tracer, except it also traces the exit of a function. So it traces where the function enters and traces where the function exits. I enable the all IRQ events. I want to see the IRQ events. So I get to see information. Remember, the function and function graph tracer don't give me any information. They just say they just tell me that a function was hit. But I want to see what event, what caused that function to be hit. What IRQ was there? So I enable the IRQ events. I go through and I turn on, the absolute time. That normally function graph tracer on the normal thing, I put this in here because this line over the timestamps that you see in the beginning, function graph tracer by default for prettiness that doesn't display. So actually I want to see the actual all timestamps there. Otherwise, this first column in the list will not show up. So actually there's options that modify the output of tracing that you go look at. Eventually, I click tracing on, and I cat trace, and here you can see the do IRQ, and this is what interrupt. This is actually on my laptop. The ACPI took off, and it tells you it took 160 microseconds to execute that handler. That's quite a lot. That's pretty big. 160 microseconds is a lot of time. It's more than 1/10 of a millisecond. So, and then you see there's other things that, a lot of them most interrupts only take 33, 20 microseconds to execute. Granted, there is a little bit of overhead within the events to record. Events, I think a last trace is about 300 nanoseconds per event, maybe a little bit more, 400 nanoseconds or so per event. So that builds up over time. So the set ftrace filter and set ftrace no trace, this is kind of like a quick overview of this. What they are is ways to limit what functions are being traced. So if you only want to trace, like I said, do IRQ, you would echo do IRQ in that thing. Say if I want to trace all functions, so I leave that empty. If this file is empty, it means either all functions, If the files are empty, it means either all functions, it means all functions basically, or no functions, because filter means all functions, no trace means no trace, no function. What I mean by that is, if I put any function within the no trace file, it won't trace that function. Because a lot of times there's locking. I want to trace all functions, but there's some functions that just are overwhelmingly, like the lock functions. I don't want to trace locking functions because they just kind of fill up the buffer. I don't care about the lock. I mean, I do care about locking functions, but usually I trace the flow. If I'm not looking for a deadlock. When I want deadlocks, then I'll do it. But if I don't want to see the deadlock, I only want to see a flow, I will disable the lock, and I will echo a command to disable all the locks, but with the no trace file, but trace everything else. If I want to specifically, so basically the way this works is it first looks at all the functions in the set ftrace filter. If it's empty, it means all functions. If it's not, it will limit to those functions in that file. Then it looks at the no trace file, and any function there, it will actually won't trace. So the no trace overrides the trace. So if you put the same function in one function, say if I put do IRQ in set ftrace filter, and I put do IRQ in set ftrace no trace, it would trace nothing. Yes.
Are these files line oriented or one function per line?
No, it's white space.
Okay.
So I could actually white space delimited.
Okay.
Thank you, I planted him. You can put there, you put multiple lines. In fact, every so often, someone, like, remember I said that all functions are traced except for things that are explicitly marked no trace? Well, there's certain key critical functions that ftrace will actually call into itself, and if it's traced, it'll actually cause a recursion and crash the machine. So every so often, in an architecture or something will happen, they say, oh, someone will add a function into a critical section that gets traced, causes the system to crash. I do a bisect of the, I could bisect to find what function is, because if you enable all functions, it crashes. If I enable a few, it doesn't. So I know some functions shouldn't be traced. So what I do is I take the set available filter functions, which is a file in that directory that lists all functions that can be traced. I cat half of it into set ftrace filter. I just cat the half, and then if it doesn't crash, I say, okay, the other half is, and then I just take the other half and give it half of that, and I go back and forth, and it takes a few iterations, but eventually I will find, that's how I find the functions that are bad. Yes?
When you're making changes like echo or whatever, when does it actually apply the change? Does it apply change whether you write or when you run the file?
Okay, so it happens on the write. It depends. If you echo 1, or say if you echo 1 into it, on the 1 it will actually usually kick it on that. On things like the filter files, no, it does it on the close of the file. So if you open it and put a bunch of things in, it just puts it into a buffer that once you close it, it clears it out. Okay. Actually, I shouldn't say no. I take that back. It's not on the close. Is it? No. Oh, wait, yeah, I think it is. I have to look at the code. Now I'm thinking, it has to be on the close. It has to be on the close because if you echo a bunch of things, it's got to enable, it enables them all, but it won't actually fill, it puts it into like it sets them up, and then on the close, then it says, okay, now execute. Because all it does is flip a bit. And what you're doing is you're flipping bits saying, we're going to properly, you're actually not saving what you're writing. It just flips a bit into the function table that lists all the functions, flips all the bits, saying that these are prepared to be updated. And then when you close the file, it then goes through the list, and then it'll actually say, okay, enable these functions. Okay. So if you have a bunch of functions, you want to add another one, you use the concatenation of bash, greater than, and if you put like a not function there, it'll actually remove it. And if you just write anything to it, it will clear the whole list. By the way, that's about all I'm going to talk about with the ftrace file system. If you want to know more, download Linux kernel and documentation trace ftrace.rst. It used to be txt, but now I guess RST is a new way of doing things. This is where all the information, basically everything I talked about now, and every option, pretty much every option, every file in there is documented in this file. So that's why I've had enough. I know people want to take pictures. I'm going to give out the slides, but I'll let you take a picture. Pictures last forever. So, ftrace is a tool for BusyBox. If you have BusyBox, you can use ftrace. So that means cat and cat echo. That's all you do. You could use it. But it's very tedious. It could be problematic, and it's kind of hard to use because you have to know all these commands, all these files, and it can be running. You have scripts and stuff like that. But there's got to be a better way. That's why I wrote tracecmd. Trace command is executable that basically it knows all about these files, and it will do all the work for you without you needing to know much about it. It reads. There's also another file. I talked about trace and trace pipe, but that's all. When you read it, it's ASCII. So trace command wants to use the binary data because it's all about speed. So since the ftrace ring buffer is per CPU, it will actually read those straight raw data, binary data, and put it directly into a file. Anyone here know about the splice system call? At 2. So most of the people here have never heard of splice. Splice is a great system call. It's not well known. It's Linux only. It's not POSIX. It's Linux only, but it's an awesome system call. Say if you want to copy a file, if you want to write a program that copy the CP program, you write it yourself. The idea is you open up a file descriptor pointing to your file that you want to copy, the source, open a file descriptor of what you want to write to the destination, and then you read into a buffer into your user space. So the kernel has to now send the data from the disk up to your user space program, and then your user space program has to turn around and send it right back to the kernel and say, move it there. That's kind of a lot of wasted time copying up into the user space and then copying it back down to the kernel. There's got to be a better way. Maybe you could memory map, that works, mmap, but sometimes there's devices that you can't mmap. What Splice lets you do is say, hey, I got a file descriptor here. I'm going to attach it to a pipe. I have a file descriptor over here. I'm going to attach it to a pipe going the other way. And in between, I'm going to call this system call Splice that takes two, or takes, well, yeah, I think it'll actually takes a file descriptor to a pipe and a pipe back to a file descriptor, so it's actually two Splice calls. And all Splice tells it is, hey, kernel, take this data, put it into a pipe, which means it just copies a pointer, so the data actually doesn't actually get copied anywhere. It says, okay, move it over here, and then, okay, now take this data here and move it into there. So it just moves the data directly in the kernel without, so the page is just a pointer to the page. It says, take this page, put it here, and it does it, no copy. So ftrace uses a zero copy for the data, for writing, when it writes from the ring buffer, and the ring buffer is made to break it up into pages, so actually it writes into the ring buffer, and the way the ring buffer in ftrace works, it swaps it out with an empty page. So it takes that page, once it's written, it doesn't copy it again, it just moves it right into the file system directory and says send it out. So trace command's really fast. To use it, download the Git repo. It's down at the bottom is the Git repo. You could go to git.kernel.org, search trace-cmd, and you'll find it in the list there. So just don't have to remember this file, but just there. Download it, git clone. Don't use, it's in distros, don't use it yet until we work on to packaging. So we get a good packaging manager, he's going to help you with packaging. Download it, do make doc, then you do sudo make install doc. I put there for most people use sudo, I don't, I would just switch user, but people say don't do that, or don't show that. I do that, just don't do it. And then you have man-tracemd. So all the commands I've talked about has been documented. So everything in tracemd, man-tracemd will show you all the commands that are available. So you want to see what the record command does, you do man-tracemd record, and it'll give you how the record works, how the report works. So again, this is not a tutorial. The information is offline. So let's do a little anecdote. Anyone here heard of config no hertz full? Anyone here a real-time person? Hey, well, we got one real-time person. Hey, okay, how about high-frequency trading and all that other stuff? Anyone here? Okay. Okay, so anyone here of no hertz? No hertz is an idle when your system goes into no hertz, or basically the idea of no hertz is if your system goes to sleep, you don't want it to wake up because of power management. You know, the longer your CPU is in sleep, the deeper it could go and the less power it takes. And of course, it takes a long time to come out of that. So the kernel has a thing called a jiffy, which is a clock tick. If you ever see how the hertz, so the clock tick. So it'll do a clock tick. So when your tasks are running, it's used for scheduling. It's used for a lot of things. It's used for timeouts, timers, networking packet, stuff like that. So a jiffy goes off, tick, tick, tick. Well, when the CPU is, when everything's idle, there's nothing to run, why have this tick go on? So this thing called no hertz that will disable the tick, and then your system goes idle, and it could go into a real idle, and that CPU may never actually ever come back online because there's no need to, because nothing's running, it doesn't have a tick, and when it wakes up again, it looks at the clock, internal clock and says, oh, and it'll fill in all the ticks. I mean, if there's supposed to be a timeout to go on, it will know as it goes idle, it will check to make sure there's a timeout, and it'll make sure it wakes up at a certain time for the next timeout. But if there's no timeout, if there's nothing on that CPU, there's nothing, no timers going off on the CPU, because if there's a timer on that CPU, it won't turn off the tick, obviously. So there's no timers, no nothing, so the CPU's getting a lot better sleep state. Your laptop on Linux lasts much better with no hertz than if you kept no hertz on. So no hertz full is, here's where the real-time thing comes in. What about a process that goes into user space? Now, all the tick is about things that are for scheduling. Really, if you don't have any interrupts going on, and you're not doing anything in user, if your process is like calculating, you know, pi to the millionth thing, and you're just doing everything in your own memory, or basically maybe you have you memory map a device, and you're just going to access the device directly and skip over the kernel, you don't want the kernel to interrupt you. So what no hertz does is if it's a single process, and you set the CPU to be no hertz, it will tell this, if this process goes into user space and there's no other thing to schedule, it will turn the tick off. So you don't have to do the tick. So it actually spins without any interruption within the kernel. It sort of works. There's a lot of other housekeeping that's going on, but it could drop the tick quite a bit for now. So let's see if it works. So Frederick Weisbecker, who is the author of No Herx Flow, put up a little test program. And in his test program, he has two things. He has a script. There's a bit of work you need to do to make sure all the interrupts and everything are not on a CPU. So you have to pick a CPU, take off all the interrupts. You got to do some work, some preparation to make sure the CPU's pristine for only one task, and then you run a task on it. And the task he had was a simple while loop. So it was main while one. One thing, I posted this little patch because I did this because I found that it was doing a lot of page faults right in the beginning. Or I mean, well, not in the beginning, but later on. Page faults are kind of scattered in because for some reason it does weird things, I don't know. So I was like, do mlock all right in the beginning, which basically says, pull in all your memory right now, don't page fault it. So everything's in the page table, so it does all the page faults in the beginning, and then it should run forever. So I executed this, and this is the command I used. Trace command. Record, because I'm going to record the data into a file. Record. If you replace this with start, it just enables it into the ring buffer or ftrace, like I did it through echo. I did it directly to the file system. But record will actually copy it to a file that I could look at it offline. Function graph tracer. -p means plugin. Okay, tracers used to be called plugins when I wrote trace command, but now I call them. But now plugin means something else. So I have tracing, but because of backward compatibility and historical reason, -p is still there. I hate it, but I don't like to break backward compatibility. So -p is plugin tracer. So function graph tracer and max graph depth. That's highlighted. It's telling the function graph tracer only trace the first function graph that you get. Instead of doing the whole scale, like tracing everything, the first function it calls into the kernel, that's all I want. I don't want you to trace anything else. So it only shows me entering into the kernel. So I'll see page faults. I'll see anything else. So I'll see a system call. I'll see any time the user space goes into the kernel, I'll see it. And I only will see that. So I recorded it, I added interrupts and scheduling, and I kicked it off, and then I said task set. That's a command to say run this user loop on CPU 3, because that's the CPU I had no hertz set to. And then I did trace command report -L means give me the interrupt status. That L will give you this little tiny thing right there. And then CPU 3 tells me I only wanted to see CPU 3. But later on, I had a bunch of stuff, and I'm looking at this, I'm like, there's a lot of text here. Why is it doing this? I want to get a visual. I want to see where times are. And I couldn't get that. It was too much text, too complex. I mean, do you see, like, okay, yeah, but that doesn't tell me what I want. I want to know how much is the kernel interrupting my user space program. That's what I want to see. Introducing Kernel Shark. So, Kernel Shark is a GUI front end for trace command. It was originally created in 2009 under GTK, but when it was written under GTK 2, but now GTK 3 is out, and I hear 4 is out now. And basically, I had a choice of rewriting my Kernel Shark for GTK 3. Finally, I threw up my hands and said, let's do Qt. So, VMware hired Jordan Kardashev, something like that. Close. I'm getting closer to pronouncing his name correct. He's working with me for that. Who is now a co-maintainer for Kernel Shark and soon will be the official maintainer of Kernel Shark. He wrote the code from scratch. I reviewed his code, but he did the grunt work. It's in the same repo as tracecommand.git, but it might change. I don't know. We'll see. And instead of doing make doc, you do make GUI, and it'll build Kernel Shark. This is what it looks like. This is what I ran on that user space. And this is where I filtered out, there's ways to filter out CPU 0. By the way, kernelshark.org will have all the documentation on how to do all this. It's not quite there yet. It still has the old GTK code in there. I have the new one out, but it's not available yet. I haven't switched over. But once 1.0 is officially released, it's still not quite released. I'm hoping maybe next week. I've been saying that for the last month. So once it's out, it'll have the documentation and everything for you. But see, okay, that line right here, I only filtered out CPU 3, and this line shows that the process is running. When it's no line, that thick orange line, it could be different colors. When there's no line, that means that there's no process running, it's idle. But these little ticks here are events that it found. So you can see that this kernel's doing something while that guy's running. Otherwise, it would be a smooth line. And I clicked marker A, and then I selected here, and I clicked marker B, and I selected here. And up here, you can see the difference in, what is it? I can't really see here. It's 4 seconds. So every 4 seconds, the kernel interrupts. So it's pretty good. Instead of doing, usually it goes off like 1,000 times a second. The tick, while the process is running, only goes off once every 4 seconds. Not what we want, but much better than what we've had. So systems could be less interrupted by the kernel for 4 seconds at a time. Then I ran something in the background on another CPU in user space with no priority. It was my own user task, and this happened. See that big blob right there? Within the 4 seconds, I get this solid line of events. I zoomed it out. They're about 12 microseconds apart. Between 12 to 16 microseconds, a tick is going off. Is that 12, or no, milliseconds, sorry, not microseconds. That's the, I would say 12 milliseconds, I would say that's pretty good size, so sorry, wrong magnitude. 12 milliseconds, still going off 12 milliseconds every time on something that's not supposed to be interrupted at all. How does this happen? I know one person that knows the answer. So, by the way, I zoomed in here. That function here that's calling all the time is this SMP call function single interrupt. This is an interprocessor interrupt. This is when one CPU sends an interrupt to another CPU for some reason. So I want to know what the heck is going. So this is the code. I actually took the Linux kernel, said here it is. Here's what the code is. And don't worry about this. This trace call here is not really a trace point. It's actually something that helps tracing within interrupts. But that has nothing to do with this talk. So ignore that line. But this guy here calls here, and I went down and I kept looking at who this guy called and this guy called, and finally I got to this file, and where it passes in this calling context descriptor. So this is the function that the other CPU asked it to call. So what is this function? I don't know. So I'm stuck. I'm like, okay, I get this IPI, some function's there, I don't know what's calling it. So I'm like, okay, let's do something different. So instead of doing max depth equals 1, I don't want max depth. I want to see the whole call graph. But I only want to see function. I only want to graph the SMP call function single interrupt. I don't want to graph anything else. So I do trace command with the -G option, and I put the function name that says graph this guy only. Don't graph anyone else. And then I ran, and I got to see it, and I could see how it called the function and followed everything, and this was where the func was. So now I could see what that func variable was, a function pointer that was passed to it, and this is the function that's called. So I grepped it, get grep, put that function in, found the file, looked at that file. It's called by 2 functions. Well, this is the file this is on the other CPU. This is what the other CPU called. The other CPU called this function and said, I want to see this. So I'm like, let's trace those functions. So this time I don't care about the function graph tracer. I only want to see those functions, and I want to see who calls it. So it's not, the graph tracer tells you what a function calls, but the function tracer with the option and trace command with this one, func stack, will give you the stack trace back up. So I can see who called this function. So now it's the other way. The first time I wanted to see what did this function call. I used the function graph tracer. Now I'm using the function tracer with the stack dump to say who called this function. So I got to see the other way. So I put in this, I said the L means the limit. This actually, the -L, what actually trace command does is writes these functions into the set ftrace filter. That's all it does. It actually takes that, it's just like cat, those function names into set ftrace filter. That's all it's doing. So it's only doing that. I put func stack, which says give me the stack trace. By the way, ftrace or trace command won't let you do it, but you could do it by hand coding. You can enable the func stack option, and you can enable all functions in the kernel, and expect your laptop or your whatever machine you do to run at Commodore 64 speed. Because every function in the kernel is doing a stack trace. That has a bit of overhead. I think like 10,000x more overhead. So do that, and it might take a while. You hit a button, I've done that by accident, and I have to turn it off. So you type on the screen, and you wait 10 seconds for the keys to appear. And then you say crap because you did a typo. But anyway, I did this function. And I looked at the stack trace, and this is who called the function that sent the IPI. And I see this proc reg open and a CPU info open. Anyone knows What application or how could I get those functions called? Proc reg open followed by CPU info open. Anyone familiar? Yes.
Somebody might be doing a cat proc CPU info.
You mean this? I ran that on the other CPU as a user, normal space, and what I found out, I just found out yesterday, thanks Brendan, that cat proc CPU info is not just a read-only function. It causes something to happen. See that CPU megahertz? Well, that's calculated. And it can only be calculated from the CPU that it's showing. So when you want to calculate the cat proc megahertz, by the way, so if I take that and if you could do it on yourself, you do cat proc CPU info and you run it again, you get a different number. Every time you run it, you get a different number. So it sends an IPI to every CPU to say, calculate this for me. Pretty inexpensive. Moving on. That was my anecdote. Back to debugging the kernel. So you have warning messages. Everyone loves this. How many people have seen this? Not many. Okay, every so often you see this. When you see this, you say, help. You get a warning message. That means something happened in the kernel that wasn't supposed to happen. And I really wanted to do an anecdote on this. But you know what? I hate to say this. The Linux kernel has improved so much because of Linux Next and all these zero-day bots and fuzz testing that I couldn't, every bug I found, I was going to go and debug ftrace and show. I actually was going to say, I've done this before. I've done this in the past. I've actually found bugs and debugged it at the conference and presented it. And I was going to do that here. But all the bugs that are available are for strange hardware that I don't have. And I went back and went, oh my God, the kernel's so solid now, I don't have to actually hit this much anymore. But if you have strange hardware, you will hit this. But anyway, so to cheat, well, first I want to talk about stopping the trace on warn on. So say if you want to enable all tracing, and when you hit a warning, you want to see that tracing. But if you the ring buffer, because they're not going to do the record a lot of times, you just care about what led up to it. So you don't want to read everything. So I'm just going to let tracing the ring buffer go, and if I hit the warning, I want it to stop, because otherwise it will blow away, and the ring buffer is only a finite resource, and it wraps around, and it will overwrite the cause. So I want it to stop so I can analyze it in the kernel, in the memory. So there's a thing in the procsys kernel, there's a few flags in the procsys kernel. If you ever do a cat of procsys kernel, you'll see a bunch of flags that have little ways of tuning the kernel. One of them is trace off on warning. You echo one in there, it will turn off tracing. So, because the Linux kernel was so bad, I said, let me just throw in a warning. So I put in a warn on once into the RT mutex set file, which says if anyone boosts a process to 99, which is the highest priority, which in the kernel is 0. It's inversed. There's a reason for that. But anyway, anyone that boosts a task to the highest priority, I want a warning on it. I don't want anyone boosting tasks to it. So basically it's priority inheritance. If a priority inheritance lock happens. So I took my migrate code that I use for testing migration of real-time tasks. It's on my home machine in migrate.c. I take this code and I compiled it. I enabled all functions. I echoed one, turning off, trace off on warning, compiled all functions. Check to see if tracing's on, enabled. Yeah, it's on. Then I ran my migrate task, passing in -p99, which says use the max priority on this, and it does priority inheritance. And what happened, boom, something got boosted, and there. It triggered, I do a cat, and sure enough, 0. Demessage tail, I see, hey, it spit something. So I'm just letting you know that that's how that works. So I did a trace command show, by the way, just to see if it did, and you can see that it's the migrate task, and it ticked off the warn on. So there, I got to see that. So if you ever want to stop tracing, that's what you use. Now if I want to look at it, like I said, I didn't have it in a ring buffer, so I'm like, I want to look it up online. So trace command extract will take the current ring buffer and put it into a trace.dat file that you could do that you could do all the functionality of trace command report or kernel shark. Let's go on to kernel panic. You know, you hit bug on, it crashes. Okay, what do we do then? Your system just crashed. There's no cat trace. So you enable all functions. By the way, if you want to test this, hey everybody, open up your laptop, running Linux, echo C into proc sys request trigger. It will crash your kernel. It's actually a way to do it. You may at first have to enable it, but if you echo -1 to proc, remember that proc sys kernel has a bunch of tune things? Well, there's one called sys request trigger to enable all the sys request triggers, and if you do -1, that enables all of them, and one of those is, I want to be able to crash my kernel. So, ftrace dump on oops. This is a way to print everything that's in the ring buffer out to the console. If you have a serial console, which very few people have today, but there's possible ways to do it. You could get it out to the console or other consoles. So when it crashes, it'll actually print out the buffer. By the way, if you have a serial console, especially if it's like running at a really slow baud, even at the, what was it, 115, what's the baud rate? That's 1152, something like that. I can't remember.
Servers have zero consoles.
Okay, most servers.
Talking to the BMC.
Yeah, so most servers, and also virtual machines have serial consoles too, so that's awesome. I do this so I put a serial console. So it crashes, but then in virtual machines you can stop easily too. Anyway, so I usually put echo 10 into the buffer size, so I shrink the buffer. So, because by default it's 1.4 megs per CPU, and 1.4 megs of data per CPU. By the way, when you boot up, it's only a few K. When you execute it, it expands the buffer. So tracing, when you have ftrace, you're not using 1.4 megs per CPU on boot up. Only when you first do anything in tracing, it will allocate the buffer there. But the default size of the buffer is 1.4 megs per CPU when you enable tracing. You could change the size of any CPU per CPU, or if you would do them all at once with this guy. So I always say echo 10, so it's like 10K. Because if you have 1.4 megs on like 7 or 8 CPUs and you trigger the ftrace dump on oops, well, maybe you'll get it by next week. So it's a lot of data to wait for. By the way, -B you could change that in trace commands. They do trace commands start -B 10 -B no op. I just set my buffer to be 10K each per CPU. So how do you enable ftrace dump on oops? It's a sys control key, another proc sys kernel trigger. So anything in proc sys kernel could be enabled by syscontrol. So you echo 1 into that, and it'll turn ftrace dump on oops, which will dump all CPUs. But say if you only care about the CPU that triggered, so maybe you're not worried about a race condition, you're only worried about what got up to that, you can actually put in =2, or on the kernel command line, orig CPU, which means that when you put 2 in there, when it triggers, it will only dump out the CPU that crashed. It won't dump out all CPUs, it only dumps out the CPU that crashed. And this is like what happens. I triggered it, and boom, and you'll get a little message there. It says, dumping ftrace buffer, and then it gives you the buffer out to the serial console. kexec kdump. How many people use this? Not enough. I love kexec kdump. It's RHEL, Red Hat Enterprise Linux. I used to work for Red Hat. Does it all the time. It's awesome. The first thing you do is you load the kernel crash memory, like 128 megs. That's where it's going to load the kernel into the memory. You run kdump control, or have systemd or whatever your init process calls it. It will actually load it up. It also creates an init RAM disk that's going to be called when the system crashes. And then finally, on a crash, your system will reboot. It will actually jump to that kernel that's loaded in memory. It's a different kernel than the kernel you're running. So your system's running, it crashes, it will jump into that other kernel. The kernel will boot up, and then it will mount the file system you tell it to, and then it will do a core dump of the entire memory into a var crash VM core, and it'll save it there. So now you have access to a core dump and you can analyze it with GDB. And I did this is QEMU, KVM. I did a little snapshot of my window alert manager of it happening, because it didn't do it over the serial. So down at the bottom, you can't really see it, but it's showing that it's actually copying it's telling you, it gives you a progress bar as it writes to the VM core into the file. Crash. Anyone hear the utility crash? I didn't put the link up. Darn it, I was supposed to put the link up. There's a link, I have a link, search crash Linux no, how would it be a good, it's hard to, a lot of these things are hard to search on Google. David Anderson, I can't remember his name, David something or other. Or CC me, or maybe when I upload the slides, maybe I'll add it in there, so when he uploads slides, I'll have the link to his stuff. Crash is awesome. He also works for Red Hat. It's a thing, so it's run like GDB. In fact, if you notice, it starts off, it has GDB, it actually compiles, if you download it and compile it, it will actually build a full, it will download GDB and build GDB for you, and it's an extension on top of GDB. It's basically GDB knowing how, all the structures of Linux. So you put in Crash, you pass in the VM Linux kernel, you pass in your VM core, and then it'll boot up, and then now you can actually, you can look, you could do LS, or not LS, you could do like a PS, and it'll show you all the processes that we're running. It's really, really powerful. I recommend learning it, but that's not part of this talk. What I did was, one day, someone asked me, Lai Jiangshang, I think his name was, he's not really a kernel developer anymore, but he when I first did Linux, he asked me, hey Steve, this trace.dot file that trace command uses, can you tell me the format of it? I said yes. Download the git tree from tracecommand.git, type make install doc, or make doc, make install doc, and do man tracecommand.dat. And that will list you the format file. That shows you that's the description of how trace command is formatted. 2 months later, I CC'd on this patch to Crash that built an extension to it. You do type, this is part of Crash now, extend trace.so. It loads it. You do trace dump -t trace.dat. It reads the VM core, pulls out the ftrace string buffer, figures out the events, creates all the event tracks, so he creates everything in there, creates the KAllSIMS file, and then creates a trace.dat file out of it. Quit, trace command report, boom. You have your data from when the crash happens, and you can pull it up in the kernel chart and see everything that's going to happen. Now, by the way, that first line here is where the crash happened. This is right here, spit out a bunch of, I guess, prints. This is where actually it went into it kicked off the kexec, and that's where the last review of it, yes, which was, can't really see, 21 milliseconds, yes.
So my question is, this all assumes that you have ftrace turned on and enabled in order to actually, looking at the ftrace buffer is only useful if you've been tracing something.
Yes.
So is this only useful for applications that you can actively reproduce kernel crashes for?
No, well the thing is, believe it or not, although you could change the size of the buffer and everything like that, there's people that run ftrace on production machines, have it enabled and recording, and they have maybe different things. So as long as you have an idea, you can actually record certain things, certain events, and it has a very, very low overhead. It's very, very fast. You can actually record an awful lot. I mean, you don't want to go full-blown function tracing, but you can have a lot of critical events, and if a crash happens, it'll spit out, and you can say, oh, you have an idea. It's another way of seeing what's happening. By the way, this crash utility, when I worked for Red Hat, there was a bank that was crashing on the real-time kernel, and they were saying, but they couldn't give me their reproducer. It was on their production machines. So I would just say, here, turn on these tracing. They were able to reproduce it, crash it. They sent me the core dump. I analyzed it, figured out, oh, the problem's between here and here. Okay, ignore everything else, turn on some different tracing. Core dump, 3 or 4 iterations, led me right to the bug.
Okay.
And it was within a week.
But you're not going to do this on healthy machines. You're going to wait until they start crashing before you turn on ftrace.
No, I'm saying people run on production machines, ftrace enabled.
Right, but only when you know you're going to be hitting problems.
No.
No? So is there stuff, you mentioned that turning on all these traces is going to blow your machine to nothing.
If you enable all tracing, yes. There's certain things, like even, like, it matters what, we have to take this offline. Yes, yes.
Just a comment, not a question, but I look like 5 dumps every day as a part of my daily life, and this is going to be very helpful because we have a special kernel module, and we can tell customers to enable traces for that module, only those functions, and then when you get a static app.
By the way, one of the features of, it's in the documentation of the set ftrace filter. You could do set ftrace filter :mod ext4, and it'll enable all the ext4 module functions only. So you actually, there's actually a command in set ftrace filter to say just base this module. Anyway, just before we get, time's almost up. In fact, I think, yeah. So have 5 more minutes. When all else fails, I just want to do one last thing. This means you have access to the kernel code and you can modify it. Trace print K. Trace print K should not be used. If you enable this, you're going to get a really nasty demessage bug that says, you are running a debug kernel. If you see this on your vendor, notify them immediately. I did that to keep people from ever enabling this internally. It won't hurt, it just, I don't like, there's a reason why. There's better, trace events are ways to do it. I don't want people to be sloppy. People get sloppy with trace, because trace print K, there's not a good parsing product. It's just a debug thing. It's like print K. Print K is like printf in C, but also print K and trace print K have special features, like you could do %ps, which will, like, if you could do %ps and you put a function pointer there, it'll actually translate it to do IRQ, bitmaps, MAC addresses, IP addresses. I put in lowercase p, capital I, that's a capital I, it looks like an L, but it's actual capital I, that's why I have PI there, and et cetera. There's a bunch of things that you could do, but trace print K, you could do, I always do the shotgun approach, which is, okay, this is my shotgun approach. So I took prepare task switch inside the scheduler tracer, and I put trace print K. The first time I actually put in some information about the parameters, so, you know, and everything else you'll see func line, I just cut and paste, I just blast it. Almost every line has this trace print K thing. This is when something crashes, I want to know, or something changes, or something I want to know exactly when it happened. So I put all these things, and then I compile the code. By the way, func line is macros that GCC will actually put in the function name and a line name. And this is what I get. This was the show. I want to see if anyone could see something here. By the way, trace print K will actually print the function name first and then the format. Why is the function name different than here? Anyone have an idea why? So you would think it's being called in a function. This is the function name that I got from the instruction pointer, and this is the name that it read from here. Yes?
Inlining?
Correct. This function, if you notice up on top, you can't really see, it's static inline. So when it gets inlined, the symbol disappears out of the symbol table. So that's why I put func in there, because it catches inline. Func is at compile time, it says, oh, you're in this function. It puts in a string name for whatever function you have, whether it's inlined or not. The KLSIMS does it from a lookup table of whatever function's available, and if it gets inlined, that symbol disappears. So this guy was called from the scheduler. It was inlined into the scheduler, so when I did that, I got schedule, and then I got actual function that was called. So that's why I always do func. Some people say, well, why do you put func there when you have the IP address? I'm like, because sometimes it's inlined, and GCC may inline something that's not said to be inlined, so be careful. Anyway, thank you. Questions? Yes? Running what? Good question. I usually don't, because CPU 0 is usually the default things. Like sometimes some machines don't even let you shut down CPU 0, but sometimes they do. I mean, it's dependent on the architecture. Really, there's nothing technically wrong, but it matters whether or not the hardware expects to have some services running. Sometimes you can't move a CPU, or you can't move some sort, like something, if an interrupt is hard-coded to CPU 0, because if an interrupt is something hard-coded to anything, usually it'll be CPU 0. So usually I make CPU 0 where I move all the interrupts to, and then move everything else off of that. That's usually the ideal way I do things. Any other questions? Okay, thank you. Oh, no, wait, yes. Right after this, I'm going to actually go, and I said I got done with this literally 2 hours beforehand, and actually I started to do a little more tweaks. So right after I get done with this, I'll post it up to the SCaLE site upload, as well as I know someone else had limits. Anything else? And it looks like it's exactly 1 hour, so thank you very much.
Boom, 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 boom. We'll give people just another couple minutes to come in so we can start, quote unquote, on time. Is this thing still on? Cool. Shall we get started? How's everybody feeling today? Y'all look punchy after a long weekend and a very filling lunch and setting up and tearing down booths and, seeing very heady or very lighthearted talks all through the weekend? Yeah. Lots of nods and lots of snoozes. That's excellent, Nobody's snoring that I can tell, so we're doing great so far. Awesome. Cool. So, for those of you who don't know, my name's Brian Weber. I'm a site reliability engineer at Twitter. Anybody else here who is an SRE? Throw your hands up. All right, no? Or production engineer for you Facebook folks. All right, close enough. Okay, what about like a sysadmin style title? Hey, cool, love that. What about anything DevOps related? Yes, no, maybe. Okay. How many of you are just like, how about managers? I want to see the managers out there. I have a lot of love and respect for managers because you do the very thankless job of putting up with people like me in mass, at scale. So I love and respect everybody who is a manager. You're all great. But that's not what this talk is about. This talk, I wanted to give a little peek into the view of the world of what I do as a site reliability engineer. So I kind of collected just a couple of lighthearted war stories, just some issues from dealing with production services. I can't talk about the really big outages because otherwise comms will come and fire me, and I don't want that to happen because I actually like what I do most of the time. So I want to cover some of the fun things I've encountered and some of the lessons that I've learned and, some just general stuff that I get to deal with on a day-to-day basis. So Seems like I may be preaching to the choir here, but what the hell, let's go for it, right? So again, SRE at Twitter for the last, it's almost 4 years now, but I've been doing stuff generally in this field for over a decade. Going back to my days of doing telephone tech support for a company that sold voice over IP systems that were, like PBX systems in voice over IP. So you'd buy this box, slot it into your rack, plug in a bunch of phones, and they'd wire up, and eventually your own network would disagree with all of this VoIP traffic going wrong, and they'd call me. And, I'd be the guy who'd start by, have you tried turning it off and on again? They'd say no, and then, well, let's go further. So that's kind of where I cut my teeth learning about how to troubleshoot systems in production, because your customers at that point were not like, 500,000 Twitter users or similar sized at other companies, but the dozen or so call center employees that are trying to make money for whatever company was our customer at the time. So those were the people who were more interested in just making sure they could do their job every day, or who were threatening to sue us if things went wrong, or who were just like, well, gee, I don't know how to clear my voicemail after I've listened to it, and the simple stuff. So while I've been working in tech, really the way that I see myself is I've been working in customer service. My history even goes back further, because I've also worked in restaurants, I've been an instructor, I've done all kinds of, I've done some sales, I've done a little bit of this and that for a long time before I actually started doing any legit tech work. And that's kind of what helped me be really good at doing tech support, because I picked up the actual tech skills along the way that I needed to. And that's part and parcel of what I'm going to end up talking about along this talk. So hopefully you can remember that, and hopefully the next time you're talking to somebody who's saying, gee, I wish I could do tech, it's too hard though, then I hope to try and be a shining light to say, it doesn't have to be. It doesn't all have to be just, a horrible blood sport for college grads. So when I moved up to the Bay Area about 7 years ago, that was when I got introduced to Python. Thank you, Facebook, for that. And I've totally fallen in love with the language. I really enjoy writing simple tools in it, which is a far change from writing god-awful Perl scripts back in the day. And that's not a hack on Perl, that's a hack on my ability as an engineer. So take that for what it is. So I've worked on all kinds of things, product support, just general services. I've worked on advertising. Right now I'm the sole SRE with the InfoSec org at Twitter. We've had SREs turn into InfoSec engineers, but I'm actually working with them as an SRE, helping the services that we do to make Twitter more secure and more private, both within the company and without, more stable and more reliable. It's been very fun and educational. And as you can see, I'm a very serious person all the time. So again, like I said, this talk is going to be just a few little short stories about things that I've encountered in my career, things that I've encountered just in the last few jobs. I mostly work with tools and services that are written in Python just because that's what I like to write. But again, Twitter, we're the largest SCaLE shop out there. So we also have lots of services that are just running very fun and complicated SCaLE code, which has its own host of complications, which I probably will not get into in this talk. And that's mostly because this talk was written as a 30-minute talk. We're out for an hour, right? Yay. This is what I encountered. You may encounter similar issues. Again, this is just to talk about kind of the spirit of what we've encountered. This is not a best practice talk. This is not talking about the absolute right way to doing things, because what's right for Brian and what's right for Twitter may not be right for what's you and for at your company. But hopefully we can all still learn from each other. I learn a ton from other people when I go and see other talks, hear about their infrastructure, And the vast majority of the time, I run back to my company and try and implement what I learned, and it's completely wrong because it just does not fit with our model. So instead, it's always best to just try and draw inspiration instead. So again, I'm no expert. I'm just some dude up here trying to give a talk. Cool. What exactly is an SRE? So I've heard a lot of people try to define this, say that we're software engineers with a different focus, and that's somewhat true. We all write code. We all write code to do very specific things. We have sometimes specific products that we support. We have specific customer sets. For me, my customers are the two teams that I directly support in my day-to-day. But they're also their subsequent customers, because for those teams, they just see me as another team member. That's how we like to do things with the embedded model at Twitter. We also kind of see the SRE org as a customer service provider for the rest of Twitter. So a lot of what we've been trying to do more and more is get together as an org, all of our distributed members, to try and make better services for our own internal company. So the MySQL team, they're almost entirely SREs. There's core infrastructure, which manages things like our Puppet infra and a lot of other things for provisioning servers. They're almost entirely SREs as well. But then there are folks like me who are embedded with teams. And so we all try to collaborate to see how can we help each other better at the company. So I don't know what your definition of SRE is, but that's kind of what I like to try to do. What we have also been doing is trying to get a better definition within the company of what it means to be an SRE. So some of what we've been coming around is coming up with better preventative measures and trying to advertise where our specific focuses are, which is knowing more about what's going on outside of the product. So my SWE teams that I support, they really know their stack. They really know what's going on. When that API calls hit, exactly what system calls go through inside the SCaLE code, what they hit in the JVM, how efficient that call is, and what it spits back out. And I certainly know a lot of that, but from a higher level. Most of what I know is what's going on outside of that. How does it deploy? How does it interface with the databases? How does it interface with other downstreams? How do our upstreams interface with us, and what do they care about? So because we have my perspective, which varies from my team's perspective, we're able to look around our own applications a lot better to kind of help make a better application for our overall team's customers. The other thing that I really need to update this slide. There was a great talk yesterday who was in this room, and I cannot remember who was speaking, who was talking a whole lot about how SRE's work often helps with reducing toil. And that's just the grudge work of doing our jobs, you know? We're constantly rebooting yet another server, constantly rerunning that one script that only we have permission to run, things like that. I finally have convinced that one team member that I work with that I should not be the only one who can shell onto a host to look for a file. And it's been a wonderful thing. So now the only time he calls me in is when it actually is broken, and that's a great thing. So this is what I try to see as an SRE. So to really shorten it up, we also look more about the stability of the service. Where is our alerts? Where are actual breaks and our failures? Where are we slow? Is it within the app or is it within our downstream? And then how do we target that? Are we running lean enough? Do we have too many systems in place, too many services in place, too much compute? Are we costing our team money or the company money? I'm adding this in about security. Are we actually locked down? Are we properly using TLS? Are we properly encrypting all of our data at rest? Are we staying up to date with all the patches that are coming in from the security team? And then are we properly scaled for the influx of traffic that's going to come in from that next new feature that they turn up upstream? Are we all ready for that? And then are we going to get woken up in the middle of the night? So in summary, before I've even started the talk. So the other thing too that a lot of people look at for SREs, and this is kind of like what I've perceived as branding of my teams, how other people often see us, is we're the crash cart people. When things break, when success rate plummets, we're often the first ones on the scene because we've done this before 1,000 times. So there again becomes the shift in tooling and perception to say, hey, how do we, instead of just being responsive to outages, prevent them from beginning? So that's what we try and do. So I've rambled on along, let's get to some stories. So I'm looking at our Slack channel, and one of our teams comes in and one of our customers comes in and says, hey, also the application that we support is that we have a local daemon that runs on almost every box in the fleet and manages secrets. It's fetched from an API that we control locally or control centrally, and without getting too far into details, just because, again, legal can't let me, we have this service that just makes sure that the TLS files and the database login passwords are specifically mounted in a secure way that only a service owner can access it on demand. It's a great service. We love it. So someone calls me up on Slack and says, hey, we can't access our files on this one host. The secrets aren't there. So what do we do? Go ahead, sysadmins, SREs, production ends, you get this call. Go ahead, shout out. What would your first thought be about when someone calls you up and says, hey, the thing's broken?
Turn it off and on again.
Turn it off and on again. What else?
What changes did you make recently?
What changes did you make recently? That's a great one. Look at the logs, exactly. These are all different things that we do. Anybody else have any fun ones you want to throw out? Check if it's true. That also, absolutely. So often you go and you look and you say, no, it's actually just there. I've been on the person saying, yeah, hey, it's broken, and I'm looking at the wrong damn host the whole time. So, of course, that's what we do. We look at the host, make sure it's true. We look at the logs. Eventually we say, okay, maybe something actually is broken. And eventually we may start looking at our own code base. And then we just keep going on to the next thing and the next thing. So I start looking at the logs and I see this. So the way that we make sure that our secrets are properly loaded on the box is we create on-the-fly fuse mounts. Who's familiar with what fuse does? Cool. So for those who haven't raised your hand, fuse is a in-memory user space file system. So it's not on disk, which means you can't like pull the platter out and visually inspect the dots and find out what the contents are. And if you shut off the server, you lose it all because it's all in memory. And it's only existing for the user in space, the user who's accessing the file and has permissions to. So for us to actually be able to do this, we write our own code that loads the Python fuse library, which loads libfuse on the host, which is a shared object library. And we go and we say, hey, it can't find that library. So I go and I inspect the code and I say, what does this really mean? I go and look for the fuse libraries and I say, oh, well, they're there. So why can't it find it? So what's going on here? So I take a moment and I say, is this really one host? This is our Hadoop fleet. They've got, somewhere north of thousands of hosts in their fleet. So one won't kill them to reboot. So I asked them, is this the only one? Because that just seems really weird and really corner casey. And they say, well, yeah, this is just the only one. And so I say, well, I've got like this huge backlog of tickets. Why don't you just punt it, rewipe it, and let's see if it comes back. Because problems at scale sometimes are just the one-off corner host. And so you can kind of get away with that. So do you wipe it off and you move on, right? Well, not always as easy as it seems. So it turns out it wasn't just on one host. It was on a slightly larger but not significantly damaging subset of hosts, in the neighborhood of less than 0.5% of the fleet. But it was still enough for us to say, okay, there's probably something systemic here. Let's take a further look. And I just said that. One of these days, I'm going to get myself out of Google Slides so that I can actually have the preview of the next slide. Kind of cool. So we found it wasn't necessarily following a deploy or a code change. The hosts, other than all being within the same Hadoop cluster, had nothing apparent in common. They weren't like all on a common feature branch or puppet branch running some sort of like weird code that wouldn't do something. So we try to dig a little bit deeper. And that's where I take a deep breath and say, it's time to keep exploring. So back to that error. We say, what is really going on in this code here? So I dive a little bit deeper, and this is where I actually start learning some stuff about some stuff. Again, I've been doing stuff in this space for like 11 years, and I find myself learning something stupid and remedial, or seemingly stupid and remedial, all the time. So this little snip of code is in the FusePy libraries, where it does every kind of system load for shared objects that it can do within the Python space. So that error was what was raised, which was looking for that specific value, which was calling that function, find library. What does find library do in Python? This, again, continuing to learn. That's where I finally, for the first time in a decade of being something in this stuff with Python, the first time I actually got to this specific function in the C-types library. Nobody's an expert, no matter what they claim to be, not even me. So what this is doing is it's looking for a shared object using common functions and common systems that are in your operating system. In this case, it was using ldconfig. ldconfig checks a whole bunch of folders on your system for shared objects and stores them in a cache. So has anybody here ever had to deal with ldconfig specifically, or specifically pick out libraries in the LD cache? I see one hand, 2, 3, okay. Still a very small number of people for this crowd. That gives me hope for the future that we're all still learning. And that's why I love coming to these conferences, because it helps me validate that I'm still stupid. Excellent. So we go and we dive a little bit deeper. Just on the broken host, I exercise the common Python calls, and I see, yeah, it's nothing there. But on a good host, there's the shared object. So let's step a layer deeper and see what's going on at the OS level. I see the files are there. So the files are there. That means somewhere in between the files being there and C-types finding them is broken. The package is installed, but ldconfig is missing a whole bunch of stuff on that broken host. I go and I repeat the exercise on the, I don't know, maybe a dozen or so other broken hosts, and it's this exact same scenario. The ldconfig was just not collecting everything on these hosts. Now, these are not my hosts. Well, again, that was our specific root cause for that instance. Now, this is where things get fun and interesting still. So these are not my hosts. This fleet was on an older operating system that we're actively attempting to deprecate. I was also told something at one point about the Hadoop effect, which is where there's a lot of weird complications and a lot of weird corner cases that come up when you spin up a massive data store fleet. That's okay. So again, it was just on a small subset of fleet of the hosts, and the only thing that we could find specifically in common about that group of hosts was that they were missing a bunch of stuff from ldconfig. So next comes the question, what do we do? We end up throwing them in the hole and wiping them off and seeing if it comes back, which is what we did to begin with. Now, we went through the explorative process because we wanted to see what is in common. Was there something systemic? We couldn't necessarily find anything systemic. So sometimes, a horse is a horse and a duck is a duck and a broken host is a broken host, and that's fine. This is one of the fun things that you get to do when you operate a large enough service is treat hosts as semi-disposable. So we were able to just reformat the hosts, reinstall them with the same slowly being deprecated operating system, because that's where they were and they wanted to be homogeneous on their fleet, and that's cool. But the problem hasn't resurfaced ever since. So, yay, that's fun. All right, so some lessons learned from this. Log spelunking is generally going to be the right place to start. Now, of course, you ask some of the questions about, like, is this still really an issue? Does this issue actually exist? But very soon you're going to get pointed at logs. I also learned a whole lot about what goes on with shared objects and with C-types on a host. This was all still new to me. And that's why I want to come share it at this level, because don't be afraid to ask the dumb questions. I had to ask the dumb questions, and now I'm sharing about it in public. This is great. So I learned all about how the shared objects become available, and I knew all about Python paths, so that LD cache totally became analogous to me, and so now I get to interpret that. And then, of course, the common lesson that we have at SCaLE is sometimes it's just as easy to throw the host away. But that's not always the right answer. So that was story number 1. Story number 2, we're going to talk about TLS being silly. So we have, I'm trying to remember what specific issue that was now. The fun of not looking at a talk again for about half a year after. So we had a new client that we were spinning up. We were turning up our services in the edge pops, which are specifically isolated. There's distinct firewall rules so they can do very limited things. So we had to do some very custom stuff so that our client could still make the TLS connections back home to fetch secrets to be able to serve the few things that ran out in the edge pops. But TLS was not terminating in our test environment. So as far as we knew, everything in the code was working and everything with the actual TLS configs that we were loading was working. So we're also trying to turn up mutual TLS for all of our API calls, top to bottom, wherever possible. Still not quite so easy with Python, but we are in the act of fixing that. Yay. Our primary API calls are all TLS, not necessarily MTLS. And what we're doing is from our remote services, we have to go through a different service discovery path. And that's really where this particular TLS function was TLS connection was happening, was to the outside service discovery system. So my first thought is, well, since that outside API system really expects MTLS, let's try and set this up. So I start looking at exactly what you need to do using the requests library to set up your certificates. And I say, okay, I can do that. And then we say, okay, you got to give it a verification path, and you put all this stuff into your request library. And you say, okay, I can do that. Put all this stuff into your client. So here is where we actually set up our client for talking to our service discovery from outside of our primary data centers. That way you can service discovery from edge pops. So I add those few lines and those few fields in to pick up our certificate information. Set up the configuration fields so that way I could just put those paths in our config, send them off to the hosts, and the host, because this is how we run our service. We put all the paths in the config so that we can change them when we need to. And then I set up my configs to load those certs as expected. Makes sense, right? So let's try it on a test. Boom! SSL cert errors. So I'm looking all through my code. I'm looking through how all my certs are set up, and I'm saying, okay, the certs are valid. They're in the right spot. And I try to connect, and it still belts out errors. I even step out of my code a little bit, and I try to do this using the standard open SSL libraries. So, wait, yeah, that's getting ahead of my slides here. So I try to set this up using the standard SSL libraries as well from the SCaLE. I load all my certs, I'm able to establish a connection, everything looks fantastic. But still, my actual API library is not working. So I keep walking, and there's where I actually show that I'm testing it. So before I actually get to my solution, I want to talk just a little word of warning. Managing TLS certificates is not easy. Managing certificates at scale is really not easy. A significant portion of data breaches and issues with leaking information in the public often have to do with certificate management issues. There's of course things where somebody just forgets to reset an admin password from admin, but oftentimes it's just because somebody didn't rotate a cert properly or accidentally committed something to GitHub that should have been secret. So this I know is something that we at Twitter have been working our tails off to make sure we do specifically correct. And that's also why we manage the service that we do, because this now gives us a model for doing this professionally, programmatically, and all other kinds of good words. So, and that's just a quote from the article. Yay. All right, so back to the issue at hand. So I verified that all my certs are on the host. I verified that they work. I verified that they work using common OpenSSL libraries, and when I just write up a raw Python client, I can load them up properly. So what's going on? So there was a couple of issues. First off, it was an undocumented feature that our outside service discovery system needed a whitelist. And it was never documented because their customer list for that feature set was literally one person, and that was the person we were providing certificates for. So I can accept that. It's like, okay, no big deal, right? But let's take that a step further. So when I'm looking at how to do TLS, the basics are I want to know where to put the files, because as far as I'm concerned from managing a host, they're files. They need to be accessed by a service. They need to be put here, owned by the right people, and then I need to drop the code on and make sure it works. So I started doing that. Dug a little bit further. Again, found everything worked. Found everything worked. Found everything worked. So, going back. So there was one issue in particular where in my test hosts, this certificate name did not specifically match the data center that I was coming from. You'll see at the end it says TYO3. So this was a test cert that I provisioned for a Tokyo POP, but I was testing this from our primary data center. But when I tried to match everything through our list of matching certificates, it wasn't in there. So eventually I figured out to put that in and try and set that up. But this gets even better. So when I added the verification fields and all that, everything was working just fine from the test host. Go back. So everything was working fine from our test host as it was set up with the appropriate certificates. So our root cause ultimately being that our certificate name was not properly in our certificate chains. So if I had put my certificates out for security review, which my sister team, the InfoSec team, actually does, they would have caught this, they would have helped me find this out better. So definitely it's important to reach out for help. And if I learned more about what I need to be doing with my certificates and got better at what I'm just supposed to be doing, then I could have been better at this position. But again, we're all sitting here and trying to learn stuff. So when I actually moved this off of the test host into production, the issue reared up again. So when I picked up my service, threw it over into an actual edge pop, nothing was connecting right, and the logs from my own API were not being very helpful. So as far as I could tell, the configs were working, the codes were working, everything was consistent top to bottom. So what was going wrong? So back to this little snip of code here. What went wrong was these lines of code here. So my config was hierarchical. So you'll notice that I was referring to tls.cert path. And my config file says resolver tls cert path. So in my test environment, we were failing open the whole time. And that's why you test in multiple ways possible, as many multiple ways as possible. So once I figured that out and we got the configs working right, then everything connected properly. I know I'm jumping ahead of myself here. Oh, I'm going the wrong way. So our bug here, like I said, that the config code that we were writing was meant to inherit dictionary-like functions, so we could walk through a config path and actually do a get. And the config files that we're collecting were effectively absent once they were out there, so they were failing open. They were not really resolving TLS at all, because they couldn't even find the files. We're just doing a get, which a get in Python returns a none. So there were other typos that I found while I was solving that problem, which I am too embarrassed to put on this slide. So just when you think that something's going to look great once you put it into production, doesn't actually mean it's really running great, because I went through a whole battery of tests before I found out that my config was a giant mess. So once we corrected all the paths, we started testing it actually out there on the remote side. Everything worked just fine. So it is still important for us as SREs to know what's going on inside our application, which I know goes against what I started my talk with saying today. So going back, I had default actions that were going on that made my test environment favorable. From inside our data center, we don't have to TLS for service discovery. And I was able to expand our log entries to show when these kind of TLS issues for service discovery came up, because the next time something out in our edge pop is unable to terminate TLS, now we can figure it out sooner. So you do your best to try and line up your test environments, both whether it's in different environments or whatever, to try and figure out what can be going wrong. Try and add what's a reasonable amount of logging to your code. Too much, you'll end up slogging through it and not finding anything right. And then even after you get all of your diffs committed and get everybody to review it, just double check over everything, because I feel like I probably would have caught some of this stuff if I was more thorough about looking at my own code. And I could have saved myself hours of troubleshooting later. So, in closing, which is still plenty of time left for us all to have a nice long break and second lunch if we want it. All right, not everyone knows everything. Again, I learned a ton of stuff about how to manage TLS in production, how to manage a Linux host in production, all along the way. I picked up all this unique bits of tribal knowledge just from talking to service owners that I was partnering with to get things working right. And being able to have those conversations was critical. And as much as I could, everything that I've implemented, I tried to write down in our corporate wikis. That way it's discoverable by other teams, which is important. Not everything is always going to be what it seems. And that's also why logging explicitly everything that you can is important. And having good logging functions. You know, we're adopting Splunk now at Twitter, and it's been amazing. We absolutely love it, because it helps us get better insights into what's going on in our logs. So if we have huge amounts of logs going over the fence, it's still not as big of a deal. Environments are different. So what looks like one way in one data center or one working environment, as soon as you drop it over the fence into the other environment, things could still totally misbehave, which is why you don't ever want to just say, it works over in Jenkins, and assume that it's good enough to throw into production. And can express itself differently in those different environments. So test on all of your different operating systems that you run in production. Test on all of your different flavors of Python or Java or whatever your local interpreter is. And just keep trying, just keep digging. You know, you're not going to exactly know everything about what you're looking at, but what you know, you can still lean on to try and dive deeper to figure out what's actually going on. And we got tons of time for questions and heckles, so thank you. And we got a mic to throw around if anybody wants to ask anything. Or if not, I'm sure there's a bar open across the street. All right, well, I'm happy to hang around for a little while longer if anybody just wants to come up and say hi.
Check, check.
All right, well, thanks for sticking around for the last talk of the whole thing. I appreciate it. Appreciate you being here. My name's Alan Ott, and I work for SoftIron, and I'm going to talk to you today about software-defined storage with Ceph. Is it too loud in here? Perfect. Okay. So a little bit about me first. I work in platform software at SoftIron. At SoftIron, we make data center appliances for storage, transcoding, and lots of other fun stuff. Stay tuned for that. We're currently shipping hyperdrive storage clusters running Ceph. So these are already going out the door, and they use the software that I'm going to talk about today. I've done work in open source in the Linux kernel. I write firmware. I've given training. I've done a lot of work in USB, and one of the things I do is I created and maintain MStack, which is a USB stack for PIC microcontrollers. And I've also done work in 802.15.4 wireless in the kernel, but it's been some years since that. So let's talk about software-defined storage and what it is first. So really, when we talk about storage, there's really only one question, and the question is, how do we not lose our data? Right? So in a world where everything's going to fail at some point, hard drives fail, whole servers fail, RAID controllers fail, and take out all the drives that are attached to them, and where hardware is mostly crap, but sometimes it's maybe not, where we have a race to the bottom in manufacturing because we want to be the cheapest thing on Newegg or wherever it is that you're buying your hardware from. We've got closed source firmware that comes from, well, who knows where, right? I mean, sometimes from China, sometimes from the United States. You know, who knows what's buried in there. Closed firmware on your RAID controller, that's a little scary maybe. Maybe in the hard drive controller, also equally scary. And the SSD controllers, right? I mean, this is where we've maybe seen the most issue, right? So with all the wear leveling and all the patented algorithms and all the complexity that goes into making NAND flash something that's actually reliable, sometimes that stuff gets wedged and your data is wedged along with it. So in that kind of world, what's the answer for storing data? And the answer is software, right? So what we're going to do is we're going to decouple all of the critical logic in storing your software from the hardware, right? So we're going to make data integrity not dependent on hardware integrity. So we can put, you know, hardware that may fail, and we can run software on top of it that'll just handle all of those failures, right? So in that case, we'll have no single points of failure, right? So your RAID controller, that's a single point of failure, right? We don't want to have that. And we want to have a system that's resilient against hardware failure. So, you know, redundancy of disks, so data redundancy, right? Redundancy of servers, so we have, you know, clusters of storage servers. And we want something that's going to be self-healing as well, right? So when hard drives fail, we want the cluster to recover on its own without having manual intervention. And of course, we also want to be able to migrate to different hardware at some point when we decide that we don't like the hardware that we have. So the extended answer is not just software, but software you can trust, right? So the people in this room at this conference, you know, for us it means free and open source software, right? Software where, you know, we can inspect the source code. You know, nobody actually does, right? Anybody in here actually inspects their source code? So like OpenSSL, you know how it works top to bottom, and there's no problem at all, right? So that's an important thing, right? It's not just good enough that you have access to the source code, but you need to be able to trust the source code. And how do you trust the source code? Well, you can't inspect every source code that you've ever received, that you ever run. But if you have source code that's developed by a vibrant community, right, where you know people in the community, you know people on the mailing list, where, you know, you've met people at conferences, and you can build up, you know, maybe not any of those people have seen all of the source code, right? I mean, who can read and understand every line of code that's in the Linux kernel, right? I mean, nobody. But you can know enough people who know enough parts of it that you can build a level of trust, right? You can't just assume that there's many eyes on the code. You want to know who those eyes are, right? And who those people are that are working on it. So you want something that's developed in a community way. You want something that's also widely deployed, right? Something that's tested, well tested, and proven, right? And you want something that's scalable ultimately because, you know, our cell phones take higher resolution pictures every year, right? And we need to store more and more data. So when hardware fails, software needs to have you covered. So backing up a little bit, right, and going a little higher level, right, we have three classes of IT infrastructure components, right, compute, networking, and storage. Well, on the compute side, this is a solved problem, right? We run Linux as our OS. Maybe some people use BSD, I don't know about that, but you know, we have solutions for that, and we know what we're doing. Networking, well, stay tuned. But in storage, this is also a solved problem that you might not know yet, but the solved problem here is software-defined storage running Ceph. So what is software-defined storage? Software-defined storage is storage that's going to be spread across multiple computers and hard drives. So a cluster, we call it, of storage. It's completely controlled by software, right? So there's no hardware controllers that's managing the redundancy or anything like that. All the redundancy and all of that kind of stuff is managed in user space completely, right? So there's no kernel components either in the cluster itself. So there's not any trickery. I mean, you have all the protections of running in user space that the kernel gives you. And so you want something also that's going to present itself to the clients as a single resource. So you have a cluster, it's a lot of computers, but it's one logical resource, right? You have software that's treating that whole thing as one logical resource. So many computers, many hard drives, single logical resource. Or if you want, multiple logical resources, it's up to you. But you don't have to do all of the maintenance and all of that kind of stuff yourself. So fault tolerance, you know, resilience. You know, you want to be fault tolerant against server failure, drive failure, and you want real-time automatic recovery. So self-healing, like we talked about. We want no downtime for maintenance. When hard drives, when whole servers fail, we want the cluster to do the right thing and be able to run, you know, maybe in a degraded mode for a while or something like that, but staying up, right? Still serving, you know, whatever it is that we need to serve. Another thing is replacing hard drives either as they go bad or waiting until it's convenient, right? If you have a cluster that's big enough, and you know, when you start doing division on mean time between failure for each hard drive, you know, hard drive failure isn't a contingency, it's a maintenance item. You know, if you have several racks full of hard drives, you know, every week, every month, you're going to have a certain number of drives fail, and that needs to be just something that is handled automatically, and so you don't have to run into the data center all the time and replace each one, right? You want them to run degraded, and then at the end of the week, you want to send an intern in there with a crash cart, right, and just replace all of them at once. So in software-defined storage, you know, we've been doing this long enough that three main interfaces have kind of emerged as the interfaces to the client. And we'll talk about all three of those things and how to use them. So the first is object. So object is typically the native format of a software-defined storage system. It's useful for OpenStack and object-aware clients. Well, what does this mean, objects? Well, it's basically a data store that's storing key-value pairs, right? So NoSQL maybe is one way to think about it. You know, you have a key and you have value that goes with it. You set the value for that key and you read the value for that key and it comes back and that's it. All just very simple. So that's kind of like the basic level of data storage. On top of that, we have block. And so block is basically a virtual block device. So a block device in Linux and Unix systems is a hard drive, right? Hard drives are implemented as block devices. Well, on a software-defined storage system, we can create virtual block devices. So these are suitable for attaching to a client machine, or they can be used as virtual hard drives for VM environments, right? So you can have a VM server, and it's serving up all of these VMs, and the hard drives for those virtual machines are all coming off of your software-defined storage cluster. In a block, for block data, the client manages the file system. So, and it can be any file system. You can put XFS, X4, whatever on there. Of course, you'll have to format it, right? But the file system is managed by the client. And then the third type of interface is file. So file is a networked file system similar to NFS, but with true high availability. So the file and how it's different from block is that multiple clients can mount the same file system at the same time, much like NFS. But we'll talk about how file is better with software-defined storage than NFS. Now, of course, we have to have redundancy, right? And so all data needs to be stored in a redundant manner. And so this is a requirement for fault tolerance against hardware failure, right? If a hard drive is going to fail, in order to still have the data, it has to be somewhere else too, right? So we'll talk about different types of redundancy as we go. So replication and erasure coding, we'll talk in detail about how those work. So let's talk about Ceph now. So Ceph is a free and open source software-defined storage platform. It was originally part of a university research project by Sage Weil in 2006. It was further developed at Inktank Storage by Sage and his team, and that company was eventually purchased by Red Hat, which is now eventually purchased by IBM, right? So Ceph was designed from the beginning to run on commodity hardware. So that includes servers, hard drives, and of course Ethernet. So all of the basic stuff. And it's also, it's released under the LGPL license, so you really have maximum freedom with it. So let's talk about some of the terminology with Ceph. The first is Rados, and Rados is kind of a high-level description of Ceph's architecture, and it's kind of a term that's a little bit overloaded, like many terms in Ceph. There's not really always a lot of discipline about vocabulary, but that's okay. I think most projects end up that way. So Rados stands for Reliable Autonomic Distributed Object Store, and really it's Ceph's architecture, and we'll talk about what the architecture is as we go along. The other is CRUSH, the CRUSH algorithm. CRUSH stands for Controlled Replication Under Scaled Hashing. So this is the algorithm and the map which determines how data is stored across the nodes of a cluster, right? So when a client writes data to a cluster, it's writing, a value for a key. It doesn't really care what hard drive it goes on, what server it goes on. That's all determined by an algorithm, and that algorithm is called CRUSH, and we'll talk about how that works. So CRUSH allows the cluster to scale, rebalance, and recover. And again, we'll cover this more. So Ceph releases are named alphabetically. So like many software projects, open source these days, we have a number and we have a name. And as we know, all the cool kids use the name. Sometimes they only use half of the name, to just show, how with it they are. So with Ceph, though, it's kind of interesting because the version numbers are somewhat nonsensical to my mind. And so everybody pretty much just refers to the releases by name all the time. So some recent releases, they're all named after sea creatures. So we've got Jewel, Kraken, Luminous, Mimic, and Nautilus. We can see some of the features that were added in each one, and we'll go through those. So Mimic is the current latest stable release, and Nautilus is in development. But there's still a lot of deployments running on older versions. And there's not really necessarily any reason for that, because it is possible to upgrade from one to the other without losing your data. And you can even upgrade individual servers at a time as you go through your cluster. So you don't even have to have downtime to upgrade a major release. So we'll talk about each client interface now. So multiple interfaces to the client. Object, like we talked about, object is typically just called Rados in Ceph. And then there's block, which is called RBD, Rados Block Device, and file, which is more simply called CephFS. So you'll see these terms kind of used interchangeably. So a single storage cluster can provide all three of these interfaces at the same time. So that means you can use a single cluster to implement your file storage, your disks for your VM server, and also your OpenStack backend, with object storage and whatever else all at the same time. So this is one of the real points of value that Ceph brings, is it supports object, block, and file all from the same software, all from the same cluster running at the same time. So let's talk about object, or Rados. So object, like I said, is a simple key value data store. In order to use Rados, what you typically do is you link with the librados library, and that has bindings for C, C++, and Python. And you write programs that use this library, and you talk directly to a Ceph cluster. And so you store data in a pool in whichever way makes sense for your application. It's your application, you figure it out, right? So when you do that, this backend becomes Ceph specific, which may be good or bad depending on your point of view, but one of the advantages of doing that is you're using the fastest method to access the data, right? So it's the lowest latency, it's the least load on the cluster, and so you have the most client throughput by using librados. So librados is great for high-performance computing applications or custom applications that need the most performance. And typically the way you'll split this up is you'll have one or more pools per application. We'll talk about what pools are. The next is RBD with block. So an RBD is an exported virtual block device. So it's like a virtual hard drive. RBDs can be used natively by Linux. So the Linux kernel has a driver that can attach one of these devices, and then after that you'll create a file system on it, and then you'll mount it, and you use it just like a regular hard drive that were attached to your system. So much like a physical hard disk. And of course the client's kernel is what manages the file system on it. So a file system can be anything that's supported by your kernel. and meets your use case. So block devices can also be directly accessed through librd. So this is another library that comes with Ceph, and librd is a client library that can access these RBD disks directly from the client's user space. So that means there's no kernel mounting necessary, and that makes this good for VM servers. So for example, QEMU has a Ceph backend which uses librd to talk to these disks directly. So now you've got user space to user space communication. You don't have to attach any of them to your running kernel or anything like that. And you get the best performance that way for your VMs. So anything that uses QEMU, libvirt, OpenStack, CloudStack, and others can make use of that. So that's a really nice thing. The third interface is file, CephFS. So file is a POSIX compliant file system. Very similar to NFS in that you mount your CephFS file system. So you just right on the command line, mount -t CephFS, and then you give it the IP addresses and your credentials, and you mount it and you talk to it just like it's any other file system. So the benefits, though, of using Ceph instead of something like NFS is that you have no single choke point, right? So NFS, if you've ever used NFS and tried to deploy it in a high availability way, you know that the protocol itself was not designed for high availability. It was not designed for any kind of redundancy or anything like that. It was designed when servers were big and expensive, and when the server went down, you had much bigger problems than your NFS, right? So, like I said, no gyrations or hacks required to get high availability. And of course, like I said before, the difference here is that multiple clients can mount the same file system, like NFS, and they can all be using it at the same time. And once mounted, the idea that you're on a storage cluster is completely transparent to clients. So this is really good for generic data storage or backup, or also for software that isn't Ceph aware, right, or isn't any kind of particular storage system aware. It just uses files. So we'll give you files. You can alternatively mount it with Fuse from user space. Of course, that's not going to be quite as fast. CephFS was really the long-awaited feature, and it became stable in Joule in 2016. This was kind of what the project was always headed to, right? And this is kind of the thing that everybody needs on some level. Object is great, block is great if you're writing your own software, but you're not always writing your own software, right? So CephFS, this was the real killer feature for Ceph. So there are still some limitations. So, for example, only one single file system is supported from your cluster. So when I say supported, I mean that, multiple file systems is there and it works, but it's marked experimental. The documentation says that there aren't any known bugs, but still use it at your own risk. And I bring this up to say that, this is kind of some of the evidence of the discipline that's used in the Ceph project for, hey, if we're going to mark something stable, it's going to be really stable. It's going to be something that you can use, something that's been proven. So you can work around this. You can use path-based authorization to partition off clients. So if you had multiple clients that you wanted to use CephFS, you could, separate them out by directory and then give each one, access to its own area. So, only having a single file system is something that can be worked around. Another thing is that there are quotas, but quotas are cooperative, which means that quotas are implemented on the client side. So if you had a malicious client, for example, you could get around quotas. So it's something to keep in mind in your data center. How much do you trust the clients? What are the clients? Or do you control the clients? Things like that. Quotas also require a 4.17 or newer client kernel. And so one thing I didn't say here, much like for RBD, there is a kernel module that will mount these Ceph file systems directly. So you mount it directly from the kernel, just like you would any other type of network file system. So let's talk about Ceph's architecture. So we'll talk about the hardware architecture, and then the software architecture, and then the data architecture. So from a hardware perspective, it's very simple. It's multiple computers that are networked together. Typically, there's a minimum of 4. So we'll talk about what those 4 are later. And typically, you have 3 networks. So the networks that you have, there's a public, often also called the front-side network, and this is used to communicate directly with the clients. So if you have a client and you're storing data on a Ceph cluster, you'll talk directly to this front-side network, and you'll talk to all of the nodes of the Ceph cluster. They don't go through one node and it does a distribution, you know, to the other nodes or anything like that. You talk directly to the servers that have the disks, the OSDs that we'll talk about, where the data lives. So then there's also a private or backside network, and this network is used for cluster internal operations. So the storage nodes all talk on this network, the clients don't talk on this network, and this is used for replication, for rebalancing, and recovery. And then typically you'll also have an out-of-band management network, so an IPMI network where you talk to the BMC. Of course, you know, this is optional, but it's very convenient. And in addition to that, the private network or the backside network is also optional. You can do everything with one network if you wanted to, and Ceph will do all of its communication over the front side network. So if you're network constrained, you know, you can always do that. If you run out of ports, you know, maybe in a pinch, you can just go to one single network. So let's define another term here that's a commonly used Ceph term. That's OSD, so that's Object Storage Device. It's somewhat of an overloaded term, again, and at a high level, we're going to use the term OSD to refer to what is basically a single disk. Now this can be different in certain situations, but you know, for high level, for right now, let's just call an OSD one disk. In addition, so now we've got an OSD, that's one disk, and we'll have OSD nodes now, OSD node or a storage node. So at SoftIron, we just call these storage nodes. We don't call it OSD nodes just to eliminate some of the confusion. So this is a computer that has lots of disks on it, right? So that's our storage node, has many OSDs. In addition to that, we have management nodes. So management nodes typically have no storage hard drives, and they run monitor and administration software on them. So let's talk about what this software is. So there's a handful of services that run on Ceph clusters on the various machines. The first one is Ceph OSD. So Ceph OSD manages the OSD. There's one instance of the OSD process per OSD, right? So typically per disk. So OSD will listen on the network, and when it'll communicate with the clients, so it'll send and receive data from the clients. It'll perform the actual reads and writes to the physical disks, and it'll also manage replication. So the meat of where most of your CPU time is spent on a Ceph cluster is in Ceph OSD. This does the bulk of the actual work. So in addition to Ceph OSD, we also have Ceph Mon. So Ceph Mon is the monitor process. The monitor process manages the crush map. So the crush map is again the algorithm and the map that goes with it that's generated by the algorithm that tells what pieces of data go on which OSDs across the cluster. And of course the crush map is going to change whenever the cluster changes. So whenever you lose a drive or whenever you add a drive, the crush map has to change. And the monitor process is what manages this change. It also communicates the crush map to the clients. And so in a Ceph cluster, you must have either one or more than two monitors. And the reason here is, you know, you typically want to have more than one. You can just have one, but now you've got a choke point, right? You've got a single point of failure. You need to have more than two, though, because in a situation where they become out of sync, they can vote and figure out which one is out of sync. So you really want to have, you know, either one or three. You know, three is the typical number that you will have, or that you want to have. Another one is a Ceph manager. So this just collects the state of the whole cluster and the statistics of the whole cluster in one place. Only one manager is actually required. Then there's Ceph MDS. So this is the metadata server for Ceph FS. So if you're going to have a Ceph FS pool, you need to have a Ceph MDS process. So this manages the mapping from the POSIX semantics of the Ceph FS file system to the objects in the object store. Right, so this is what kind of converts, you know, paths and file names and all of this kind of stuff into objects that actually get stored in the cluster. So you only need one of those if you're going to use Ceph FS. Another thing you'll see is RADOS Gateway. So RADOS Gateway implements a gateway or a translation between S3 and Swift APIs. So if you have applications that are already coded to use S3 or Swift, you just turn on this RADOS gateway and you talk directly to it, and now you're using Ceph without very much effort. So this is of course optional, only if you're using S3 or Swift applications. So how is the data architected? So data on a Ceph cluster is organized into pools. So pools are essentially logical partitions for storing objects. You'll have multiple pools per cluster. Admins can create or delete pools at runtime. So a pool is basically just where some data exists that one application typically will use. So each application, if it's RADOS or if it's RADOS, typically you'll have a pool per application. There's typically one pool that manages all of the RBDs. So that's pretty easy to set up. And then for CephFS, you'll have a data pool and a metadata pool that manages the entire CephFS. Each pool has its own storage profile, and we'll talk about the storage profiles later, replication and erasure coding. And so basically you can support completely different classes of data on the same cluster with different pools. And this is one of the benefits of Ceph. So placement groups. Anybody have the fun of dealing with placement groups yet? So a placement group is a logical mapping to a set of physical OSDs where an object can be stored. And I'm not going to talk about placement groups. This would be a great topic if we had another hour to talk about it. But I would point you to the documentation at the Ceph website on placement groups. There's a very long document about what placement groups are and how to compute the number of placement groups that you need. Suffice it to say that placement groups are unfortunately an implementation detail that has made its way all the way to be user-facing, unfortunately. So in some subsequent releases, placement groups are going to be better handled, and then eventually they're going to be handled automatically. But right now it's still something you have to deal with, but we just don't have time to deal with all of that today. So let's talk about a couple of storage backends that are supported. So you might see references to these. So Ceph supports two storage backends. One of them is file store, so this is the older backend. And this stores data on OSDs in an XFS file system. So it stores the data as XFS files. It requires a journal drive for best performance. File store is now the old one, right? And everything now is moving toward BlueStore. So BlueStore is the new backend. It writes data to the hard drive directly, so there's no intermediate file system. So it writes directly to the block device on the OSD disk. There's still an SSD recommended for the write-ahead log and for the BlocksDB database. So this is if you're using spinning hard drives. If you're not using spinning hard drives, you don't need an additional SSD, of course. So we'll talk about, well actually no we won't. So yeah, so with BlueStore, and this is one of the kind of the edge cases about when we say, an OSD is one hard drive. Well, really it's one hard drive, and if you're using BlueStore and it's a spinning disk, you really want to have a little piece of an SSD also with it. So that'll just give you the best performance. You don't have to have that if you don't want to, and it'll perform nearly as well in many workloads, but it is something that's still recommended. So BlueStore is faster and it's recommended over FileStore. So for any new Ceph deployment, you definitely want to use BlueStore, but you might see FileStore on older clusters. So of course, as far as hard drives go, there's always a consideration, do I want SSDs or do I want hard drives? SSDs are going to, of course, be faster and more expensive, a lot more expensive, and consume less power. Hard drives are going to be cheap and dense and use a little bit more power. But if you use hard drives, of course, you're still going to need an SSD in the system for the write-ahead log and the BlocksDB. So on our soft iron clusters that do spinning hard drives, we'll have 12 hard drives in one chassis, 12 spinning hard drives, and we'll have 2 SSDs that go along with that. So that's a ratio that seems to serve us pretty well. And so one SSD can serve as the write-ahead log and BlocksDB for several hard drives. So for example, like in ours, we have 12 total, 2 SSDs, so it's, one serves 6 drives and the other one serves the other 6 drives. And also, it's best to use the same type of solid-state disk or hard drive throughout an entire cluster. You can do stuff, you can get creative with, JBOD type configurations. It's just not going to work as well that way, and you're going to spend a lot more time scratching your head. So if you're building a cluster up from scratch, put the same type of hard drive all the way through it, same type of SSD or hard disk drive, same size and all that kind of stuff. So let's talk about storage profiles now. So Ceph supports 2 different storage profiles. So yeah, question.
You mentioned in one slide that there is no kernel component, and subsequently you said there is a kernel component. So which part of this architecture pieces needed is kernel component?
Right, so the question is, in one slide I said that there is no kernel component, and then in another I said that there is a kernel component. So there's no kernel component on the cluster side. So on the storage cluster itself, you don't need any special drivers or anything like that to implement a Ceph cluster. All those Ceph processes that we talked about, the MON and the OSD and all of that stuff runs purely in user space, okay? On the client side, though, if you want to mount a Ceph file system as CephFS, that's of course going to need a kernel driver in order to do that. The same way that NFS does, the same way that mounting an actual physical disk requires a driver. There is a driver to mount the cluster's virtual hard drive or file system. So does that make sense? All right. Whoops. Okay. 2 storage profiles. So the first is replicated, the next is erasure coded. So the first storage profile, replicated pools are very easy. So if you want to have redundancy with a replicated pool, basically you're just storing multiple complete copies of each block that the cluster is storing on the cluster, right? So multiple complete copies, that's your redundancy. It's very easy to implement, it's very easy to understand, and it works really well. So in the typical case, 3 is kind of the standard, and it's also the default. So that means each piece of data on the cluster is stored 3 times. So it's stored on 3 different OSDs, and that's actually 3 different OSDs on 3 different servers by default. And that stuff's all adjustable. We'll talk a little more about that in a minute. So this implies, now if you're using this triple replication that way, that your cluster can actually store 1/3 the amount of data that's available on the physical disk. So if you have a 1 petabyte cluster, that means if you're using triple replication on all of your pools, you can store essentially 1/3 of a petabyte. But that's the price you pay for redundancy. So 3-way replication like this is fault tolerant. So it means that you have to lose 3 OSDs at the same time in order to actually lose any data. And like I said, Ceph by default will store each copy on a separate OSD and then OSDs on separate nodes. So this guards against whole node failure. So if you had a system where you stored it on 3 different OSDs that were on the same box, you lose the whole box, well now you've lost your data, right? Your redundancy didn't really help you. So these failure domains are actually configurable too. So in addition to being on a separate box, you can configure it to store on a separate rack. You can have it store on a separate row, on a separate data center, etc. And if you wanted to do that, if you had a cluster that was big enough, you could configure the cluster to say, hey, these boxes are part of this rack, these are part of this row, these are part of this data center, etc. And then you could set up policy in your replicated pools to say, hey, I want stuff in this data center, I want it also in this data center. So whatever kind of replication you want, whatever kind of redundancy you want, and of course are willing to pay for, right, in multiple data centers and high-speed interconnects between them, you can configure Ceph to give you. So for replicated pools, what happens when you write? So we're going to talk about writing, reading, and recovery. So with writing, when you write to a replicated pool, the client will make a write to 1 OSD over the public network. So the first thing it'll do actually is it'll consult the crush map. It'll figure out where it needs to write to, and it'll write to that first OSD. So it only writes 1 time on the public network. So then the OSD process will write the data to its disk, the disk that it's managing, and then it will replicate that data to the other OSDs that are part of the same placement group over the backside network. So with triple replication, your client will write 1 time to the first OSD, and then that OSD will replicate to the other 2 OSDs. So that means that for writes in 3-way replication, twice the work is done on the backside network as is done on the front side network, right? So you send the data once, and then it replicates twice on the backside. Yep.
The backside synchronous side, or is it asynchronous? Does the client wait for all the 3 writes to finish?
Yeah, so the question is the backside writing done in a synchronous or asynchronous way? And that's configurable. By default, it's synchronous. So everything in a Ceph cluster is designed to be to preserve data integrity, right? So by default, it's synchronous. So you write, and it writes it to its own disk first, and then as soon as that's done, after that's done, it'll write to the other disks, and you won't get anything back until it's written and committed to all 3 disks.
Is the triple replication the reasoning why you have to have a minimum of 4 hosts? Because that requires 3 at any given time. You need 1. If you start with 3, you don't have triple replication anymore.
That's right, and so the triple replication being the default is the reason for a minimum cluster size being 3. And we're talking about for production kind of stuff here. You can make a Ceph cluster with 1, right? But you don't really have any of the benefits of the fault tolerance that you get.
If you're writing to 3 and that's requirement, and you lose 1, do your writes then hang because you don't have a 3rd one to write to?
Yeah, so the question is, if you lose one of the nodes and you try to write, and it's going to try to get, are the writes going to hang if you don't have 3 separate storage nodes to be writing to? The answer is no, but your cluster will go into a degraded mode. It'll be warning you. It'll say, hey, we're writing data and we're doing the best we can, but we're not able to meet the minimum constraints that you've specified.
Is there a timeout for that though? Because it'll try the 3rd one, fail, and then let you know about the degrade kind of?
The question is there a timeout for that? Well, like a timeout for noticing that a server has failed, something like that?
Yeah, I guess if it's noting that the server's failed, it won't even try to do it, it'll just be degraded like that.
Yeah, so if you try writing, to a server and it doesn't work, then it's going to know that pretty quickly, right? And then it's going to mark that server as being offline, and it's going to try to create additional replications on the servers that do exist. And if you only had 3 and you're going down to 2, now you're in the degraded mode of, hey, we can't even get this to 3 different servers. But it'll still work. It'll still work and it'll keep chugging along. But your management tools will tell you, show you warning basically, right?
During the rebuild, how much resources decrease?
So the question is, during the rebuild, how much in the way of resources are decreased? Well, it depends on the size of your cluster, right? The bigger your cluster is, we talk about scale out, right? The bigger your cluster is, the better everything works, right? Rebuild is one of those things. So you have a lot more bandwidth, front side and back side to work with. So the question, as always, is it depends, right? In addition to that, rebuilds happen at a much slower rate than reading or writing to the cluster. And the reason for that is because the cluster wants to keep the client-side network operating as fast as it can. So rebuilds just happen slower, and you can adjust how much slower you want them to operate. So if you want stuff to rebuild fast, you can do that at the expense of bandwidth on the public side. So there's a lot of knobs that you can turn, sliders maybe, depending on your UI, I guess. All right, so let's talk about reading. So in a replicated pool, reading is much easier than writing, right? And the reason is because you only have to read it from one stored copy. You've got 3 copies, you've only got to read it one time. So you basically just got to communicate with one OSD, the one that has the data, and read it straight off of there. So the client reads directly from the public or front side network, and reads are typically also going to be split across multiple OSDs. So if you're writing to a file on CephFS or something like that, or multiple files, those are going to be split across lots of different OSDs. Of course, that's going to increase parallelism, and increasing parallelism in this case is going to increase performance. And of course, because of this, for replicated pools, the backside network is not used at all for reading. So it's kind of fun to do performance testing and watch things like IFTop on your networks, and you can really see things like that. So you'll really see the network be completely idle. So the third case is recovery. Well, recovery is pretty easy in a replicated pool. Whenever an OSD is lost, after the crush map is recomputed, data is simply re-replicated from an existing copy that already exists, right? So if you have 3 copies, you lose one. After it recomputes a crush map, it just copies from one of those onto another one, and now you're back up to 3. So no drama. So replicated pools are really good for general purpose, read more than write use cases. right? So writes are kind of slow, so you got to write 3 times. Reads are fast. So let's talk about erasure coding. Erasure coding is the other type of storage profile. So erasure coding, in the general sense, is a method of encoding data such that it's resilient against erasure of part of the data. So erasure coding is something that's very commonly used in so RAID 5 and beyond, and it uses the Reed-Solomon algorithm. So the way it works is that data is split effectively or evenly into k different what we call shards. So if you have a block of data, it's going to be split up k times. And so in addition to that, we'll then generate mathematically m different additional shards of parity data. So then all k plus m shards are going to be stored. And then the original data can be regenerated or recovered as long as you have any k of the shards, right? So if you lose some of the original shards and you have the additional m shards, you can take, any k of those shards and run the algorithm in reverse, run the math in reverse, and you can recover the original data. So this means you can lose up to m of the total shards and still be able to recover the data. So how is this data stored? Well, each shard is going to be stored on a separate OSD. Of course, you don't want to lose one OSD and lose a whole bunch of the shards, right? And then now you had all this system for recovery and you can't do it, right? So it's stored on separate OSDs. And performance-wise, performance on erasure coding is actually kind of interesting. So generating the additional m shards is computationally expensive, but for typical erasure coding profiles, we'll talk about some of those in a minute. For typical erasure coding profiles, less total data is actually going to end up being stored on the cluster. So that means you'll end up with better performance on writes. So you have to do a little bit more CPU work, but you don't have to do nearly as much disk work. So your write performance is increased. So what about the reads? Well, let's talk first about the best and the typical case. So in not very many places is the best case the typical one, but in this case, that's what we have. So the best and most typical case is one where all original K shards are actually available. And that's a healthy cluster. I mean, statistically, that's going to be almost all of the time, right? Well, in that case, you don't have to do any math. All you have to do is read all of the shards, the original shards, and assemble them and send them back to the client. However, there's still a little bit more latency involved with this, because since all of the shards are split across multiple OSDs, the first OSD that you ask for the block is going to have to request all of those shards. It's going to do this over the backside network, and then it's going to assemble all of those shards, and then it's going to send them back to the client. So this is a higher latency operation, because you've got to go to one OSD, the OSD has to ask for the others, and then it's got to come back to the client. So you're going to have less total read speed. In addition to that, because you're doing more smaller reads versus one large read, right? So for a replicated pool, you just read the block directly from one OSD and you're done. Here you have to read it from multiple and you're doing smaller reads.
So you don't have a master, let's say, metadata thing that will tell the client, here are all the pieces, go get them.
Right, so the question is, you don't have any master metadata something telling the client where all the data is. That's right. So all of the storage profiles, whether it's erasure coding or whether it's replicated, are all handled by the cluster itself. The client has no knowledge necessarily of what a storage profile is. So you don't need to know. Yeah, it's all handled on the cluster side. So erasure code, recovery. So this is the worst case, right? This is where we have to do all of the math or maths. So if some of the K shards have been lost, they need to be regenerated. They need to be recovered, right? And they need to do this, they need to be recovered using the remaining K shards that still exist, and then also the M shards that have been generated, the parity data. So this involves inverting some matrices and doing multiplication. So this is a computationally expensive thing. And there's two cases where you're going to end up in this worst case. So that's recovery, right? So what recovery is where the cluster has determined that a hard drive is bad, so you've lost a couple of shards, or one shard in that case. Maybe you've lost a server, you've lost data there. It's going to go into recovery, and it's going to do recovery on its own. So what it's going to have to do there is it's going to have to recompute the missing shards, and then it's going to have to restore those shards and move them somewhere else to good hard drives. The other case is reading from a degraded placement group. So that is one that's in process of recovery. So it'll handle recovery automatically, but if you try to read something that's being recovered, well, now you're going to have to do this extra work additionally here too. So again, I mean, recovery is just something you have to deal with. It's not the best case, it's not the ideal case, it's a statistically small amount of the time, or smaller amount of the time, you know, but it's something that's going to happen. So with erasure coding, did you have a question?
Yes. The sharding, is it done based on the device transfer size for each OSD separately, or is it a global value that shard should be of size X?
Yeah, so the question is how are the shards, how is the shard size computed? So I don't know for sure the answer based on what you said, but you know, for each block, for each thing that's stored, it's split up K different ways, whatever your K is, however you've configured it. That's what we're going to talk about here. So the question is, you know, I think your question comes into like, you know, if you have a block of a certain size, is it going to be split into multiple logical blocks and then sharded? I don't exactly know the answer to that. I want to say no.
And also because the different types of storage, physical storage disks will have different max transfer size. So if you shard bigger than the maximum lowest possible way of transferring it to the controller, then you have more chances of having to do it with recovery and stuff, because that's the IO space. IO won't fit the half size of your block. So they fit basically at the whole block is either written or not written.
Yeah, so the question is the shard size have anything to do with maybe the block size of the hard drive? And I don't know the answers to it on that level. All right, so with erasure coding, you set up your K&M, and you set up your K&M per pool, right? So you get to decide what values of K you want to have and what values of M you want to have. Each pool can have different values, and of course also each pool, you know, so you can have some pools be erasure coded and some pools be replicated if you have different classes of data that you're trying to store, right? I mean, you can have some of it that's backup data, and you can have some of it that's high performance data on the same cluster, and you just have them in different pools. You know, you might have one erasure, and you might have one erasure of a different profile. You might have, you know, one that's replicated, you know, for example. So different pools for different classes of data.
This should belong to a single pool. You recommend that one, or they can belong to different pools?
So the question is, do disks belong to a single pool? Not typically, no. You may be able to configure it that way. We don't.
So this could belong to several pools?
Yeah, you'll have multiple pools be represented by one disk, for example. So you might have like 100 OSDs, right? And you know, let's say you have 5 pools running on that cluster. It's not specifically split, you know, that these disks service this pool and these disks service this pool. You may be able to set it up that way, but I don't know. I don't know if you can, and I don't know why you would want to necessarily. But
the ones that are erasure coding, the disks under erasure coding will behave differently than the disks under replication.
So the assertion is that the disks will operate differently whether they're erasure coded or whether they're replicated. The disks don't. The OSD process will either erasure code or it will replicate, and it's just storing blocks on the disk. It's all managed by the software, remember. It's up at a higher level than the disk. But yeah, I suppose it's possible to do that kind of partitioning. I just don't know, and I haven't done it.
Selling from CFS, you directly manage disks, and you create a pool with a disk, and they're going to be either RAID 3, RAID Z, rate 5 and so on.
Yeah, so
This is different.
yeah, the comment is that this is different than ZFS. Yes. All right, so how do we select a profile for erasure coding? And basically we're saying, how do we select the K and the M, right? So let's look at them separately and then look at them together, right? So for the M, so the M is the number of additional parity shards, right? Higher M, so more M's, is going to give you more resilience, but it's going to cost you more disk usage, right? And it's going to be slower. And so remember, M is the number that we can lose and still be able to recover. So the more M's you have, the more resilience you have. That's all there is to it. But you have to store more data, you're going to use more disk. It's going to cost you more money, right? So the lower the M, the less resilience, less disk usage, and also it's going to be faster because you're writing fewer bytes to the disk. So what about K? K is a little bit more involved. So remember, K is the number of shards that a block is going to be split into, right? So the higher your K is, the more shards that it's going to be split into. Of course, the higher your K is, the smaller the M's are going to be also, right? Because they're all going to be the same size. So if you have a higher K, more blocks are going to be affected by each failure. And when I say each failure, I'm talking about each hard drive failure. You have a hard drive failure, it's going to affect more blocks. So you'll have more things that you have to recover. So that's going to be a lower MTBF before going into recovery, right? Of course it will recover, but it's just going to have to do more work every time it does recover. The lower your K, the data is on fewer OSDs. The shards are each bigger, right? But now fewer blocks are going to be affected by each failure. You lose a hard drive, fewer blocks are going to have to go into recovery. But with the lower K, your M's are going to be higher also. So your additional parity shards are going to be larger. And then of course the ratio here, the M to K ratio, the higher the ratio of M over K, the more resilient but the more disk space you're going to use. So let's look at an example. So a typical profile, 6.2 is a good starting point. So that's K of 6, M of 2. It's oftentimes represented that way, just 6, 2. So that means that each block is going to be split into 6 shards, and then there's going to be 2 additional shards that are going to be generated as parity data. All 8 shards are going to be stored. And so a system like this is going to be resilient against the loss of any 2 shards. So that's 25% of the total data that's stored, right? And it's going to use 1.33 times the disk space of the data that you're storing, right? So if you're storing 1K, it's going to cost you 1.33K of disk to store that, right? So that's not actually too bad, right? That's a whole lot better than the triple replication, than what triple replication would use, right? Because triple replication, you're going to use 3 times the block size. So 5.3 and 4.2 are also commonly used in Ceph. And of course, when you set this up, you're trading off performance, resilience, and density for your specific workload. So if you wanted to, you could go all the way to like 28 and 2 or something like that. You're split up a lot of ways, and you're only storing a very small amount of parity data. So, and remember, what you're guarding against here, since the system is self-healing, right? What you're guarding against is the loss of multiple hard drives at the same time or within that window of recovery, right? So you lose one, you go into recovery, and before that recovery is over, you lose one of the other ones, and then before that, so now you're kind of at another level of recovery, you lose another one within that window. That's what you're guarding against. So what are use cases for erasure coding? Well, the use cases here are for write-heavy workloads, right? Because writing is going to be faster because you're writing less data than with a replicated pool. So write-heavy workloads are going to be better. So a lot of times there are statistically write-only workloads, right, which also need density. So a backup is a good example of this, right? Users want to be able to back up their data quickly, and in many cases, they don't really care how slow it is to read their backup. They're really just happy that there's any backup at all, right? So in that case, backup is, statistically speaking, a write-only workload. So write-only workloads are perfect for erasure coding. Another thing is scientific applications where the data is generated and it's written very quickly and then analyzed offline later over maybe a period of weeks and months. You have an experiment that runs in a few seconds, you collect tons of data, and then you write research papers for the rest of your life with it, right? So, just a little plug for soft iron. Okay, so.
In the previous slide, can you get crazy and use both of them at the same time if you really want more resiliency? Because the erasure coding will prevent you from partial reads or writes, whereas the replication, the 3 times, would prevent from a complete storage, control of failure type stuff.
Yeah, so the question is, can you combine erasure coding and replication? If you can, it's not something that I've ever heard of or read about, but you really don't have to, right? So if you went back and you wanted to have some combination, I guess, so to speak, you could generate that with different levels of K&M on your erasure coding, right? So let's say you wanted to have something that was like triple replication, right, on erasure coding. So what if you had a K of 6, but then an M of 12, right? That would essentially be using the same amount of data. It's almost nonsensical to go that far, though, right? So I mean, I think that might kind of answer your question. Combining the two is not really something you'd really want to do. But what you can do though, if you did really want to do that, let's say you had, and this is something we didn't talk about, but you can have multiple clusters that replicate one another completely, right? So you can have something in one data center and then in another data center, and you can set up policy so that everything that's on this one has to also be on that other one over there, right? And so you set up. That's what I was saying. You can set up the failure domains, right? So between OSD rack or OSD server rack, data center, rack row, data center, etc.
I was thinking in the replication where when you write the first primary copy, and when that primary copy is used to replicate to the other 2 copies, if that primary copy is written incorrectly, like partial write or partial read type stuff, then this erasure coding can help the other 2 copies to be
Yeah, so the question is, in replication, when you write the first copy and it synchronizes that to the first disk, if something were to fail in that case, then you're saying you would...
Then that copy will be used to do the other 2 replication, right? Not the original one that came into the line.
So you're saying, yeah, so if that write failed and it was corrupted, then what would be written to the other, what would be replicated? So I haven't looked at the code for this specific thing, but what I would imagine is what gets written to the other OSDs would be correct, because it's going to write it from its original RAM buffer, not from what it's going to read back off the disk, right? So, yeah, so I guess maybe at a higher level, there are many different types of hardware failure, right? And so one of the things Ceph does is it protects all of the data that's written with stuff like strong hashing, for example. So you know if something gets written incorrectly, and then you'll know when you try to read that back. Actually what you'll know, where you'll really know that is when it does a scrub. So you can set up an interval to do a scrub, and when it does a scrub, it just checks all of the data on the disks. It checks all the hashing, and it checks and just make sure that everything's consistent. So that if you start having failures like that, you can find them hopefully in a scrub, but you'll also find them when you try to read back. So when you try to read back and the hash is wrong, well then you know that's bad. You mark it bad. You go to one of the other ones, you try to find it, and say, okay, well now we need to move this data and replicate it again, because now we're down to 2, for example. So 2 minutes, I think I'm being told. Oh, is that what you're saying? Okay. All right, so I'm all the way to the end here. Just a little plug for us, the soft iron advantage of using some of our hardware for Ceph. So soft iron makes storage clusters for Ceph. We only sell whole clusters. Ceph runs on commodity hardware like we've talked about, but wouldn't it be better to have a vendor that knows about Ceph, that can talk Ceph with you, right? An integrated solution for hardware, software, OS. We find a lot of people, they come to us after they've tried to do it themselves several different ways, right? First is white box, second is you know, something from Supermicro, and then after that, something from Dell or HP or whatever, and, you know, they still haven't really solved all their problems, and then they're talking to us, right? And so we can deliver a completely integrated solution, hardware that's tuned, and not just tuned, but designed from the ground up for your use case, right? Designed for storage, designed to do the things that Ceph needs to do, right? You know, we know about you know, having hard spinning disks and SSDs, and we've built them just that way to have the right balance for that. You know, things like that. Updates that don't break your system. You know, we have our own Linux distribution, and when you do an apt update on it, you know, we've tested running Ceph that's on there the way that you're running it, right? You do it yourself, you know, maybe you got, you know, Debian or Ubuntu or something like that, and you're pulling Ceph maybe from somewhere else, pulling it from upstream, and, you know, you end up with a combination of things that haven't quite been tested right. You know, we're testing exactly the same way you're running it. We've got administration tools to make it easier. We're rolling out some pretty exciting stuff this month, so you don't have to be a Ceph guru to do some of the basic tasks, adding servers, adding drives, doing the basic maintenance. We also provide gateway services for common protocols. So one of the things we didn't talk about here is that your customers show up and they say, yeah, well, we have Windows, and we don't have a CephFS driver in our Windows. We need NFS. You're like, you have this beautiful distributed system and you want to use NFS on it. But, you know, sometimes you need to do that, NFS, SMB, and we have services for implementing all that stuff in a high availability way. So you can just turn it on and now you've got high availability NFS without very much drama. And support that's familiar with your use case, right? We know what you're trying to do. We can have spares stored on site, hot spares in the rack, and a lot of flexible payment options. Also, we're hiring, so rock stars welcome. Send some email. And so that's it from me. I think I got one more question. Go ahead. Is there LDAP integration? I do not know. Yeah, we didn't really talk about authentication in this. That's a kind of a whole separate thing, but yeah.
Another quick question. Have you used your Ceph in any HPC environment?
Have we used it in HPC environments?
Or has it been set up or tested in HPC? CERN? At CERN?
Yeah. Question is Ceph used in HPC environments? And the answer is yes. Yeah.
UCSD?
Oh, you see
Yeah.
that?
And
Yeah.
they're using Rook on top of that? Yeah.
And so the comments are, you know, CERN, UCSD, yeah, plenty of others.
That's integrated with Kubernetes.
Yep. Questions?
Yeah.